Welcome to the sleep science space. I'm really glad you wandered in tonight. Before we ease into the topic, I'd love to know where you're listening from. Maybe you're curled up in a quiet bedroom. Maybe you're drifting through the dark on a late night train. Or maybe you're settled into a warm couch with a cup of tea cooling beside you. Wherever you are, I hope you feel safe, unhurried, and ready to let your mind slow down. And if these calming explorations help you rest or simply keep you company at the end of the day, a like or a subscribe gently lifts this tiny channel along its path. To those of you already supporting it, thank you more than you realize. Now, I'll do my best not to make tonight's topic so fascinating that it pulls you back from sleep, but if it does, at least you'll come away knowing a little more about why particles sometimes behave like waves and why the universe appears to hesitate until someone is watching. A small price to pay for a restless night. So let's settle in. What exactly is quantum physics, and why does it often sound as if reality is improvising as it goes? The everyday world we move through feels steady and predictable. Drop a teacup and it falls. Flip a coin and it lands. Close your eyes and the moon doesn't disappear just because you aren't looking. But at the beginning of the 20th century, scientists started peering much deeper into matter, far beneath the scale of the familiar, and what they found didn't behave the way anyone expected. Light, for instance, refused to choose a single identity, behaving sometimes like a spreading wave, and sometimes like a concentrated particle. Tiny bits of matter appeared to exist in several possible places at once until someone checked, and the simple act of observing something didn't just reveal its state, it seemed to influence it. These weren't mistakes or faulty instruments. The results were clear, repeatable, and they quietly unraveled the comfortable structure of classical physics that had stood for centuries. Quantum physics wasn't just another branch of science, it was a different way of seeing reality altogether, a shimmering landscape where certainty dissolves into probability and cause and effect don't always line up the way intuition insists they should. Tonight we'll drift gently through that landscape. You don't need to memorize names or understand equations. We'll move slowly, softly, one idea at a time, from the puzzles that first nudged scientists away from their old assumptions to the questions that still keep physicists awake today. So settle back, close your eyes if you like, and let's begin exploring a world where the vacuum isn't truly empty and where the truths we cling to are not absolute but likely. At the start of the 1900s, physics felt almost finished. The laws of motion were tidy, thermodynamics was orderly, and the behavior of light fit neatly into Maxwell's elegant electromagnetic theory. Many believed the big mysteries had been solved, leaving only a few stubborn details lingering like dust in the corners of a perfectly swept room. One of those details involved something deceptively simple: what happens when you heat an object. Warm a piece of metal or a lump of coal, and it glows first red, then orange, then white as the temperature rises. This glow, known as blackbody radiation, came from the way heated objects emit electromagnetic waves. It was easy to observe and should have been easy to explain, but the math refused to cooperate. Classical physics, using its trusted equations, predicted something absurd. As the temperature increased, a perfect black body should produce more and more energy at shorter wavelengths, especially in ultraviolet light. The equations implied an infinite amount of energy at high frequencies so bizarre that physicists nicknamed it the ultraviolet catastrophe. A problem so impossible it signaled that something fundamental in their understanding was missing. Classical physics was adjusted and readjusted, but no matter how many tweaks were made, the equations kept spiraling into absurdity. Reality simply refused to match the predictions. Something fundamental was missing, and this is where Max Planck stepped quietly onto the stage. At the end of the 19th century, Planck was known as a thoughtful, conservative physicist. He wasn't the kind of scientist who went looking for revolutions. He trusted the classical worldview deeply, but he was also practical. When faced with the stubborn blackbody radiation problem, he made a bold move, one that didn't feel bold at the time, but would change everything. To repair the math, Planck proposed an idea that sounded almost unnatural. What if energy didn't flow continuously? What if it came in tiny, indivisible chunks? The smallest units possible, like coins you can't split any further. He called these little packets quanta. It was a radical shift away from the smooth, uninterrupted world of classical physics. Instead of energy flowing like water, Planck imagined it arriving in small steps, each tied to the frequency of the radiation. He even introduced a new constant, now known as Planck's constant, to describe the size of those steps. In everyday terms, it was unimaginably tiny, but in the equations, it was elegant, almost magical. And when he inserted this idea into the calculations, something remarkable happened. The runaway infinities disappeared. The predictions lined up with experiments. The dreaded ultraviolet catastrophe dissolved. The math finally made sense. But the surprising part is that Planck himself didn't entirely believe his solution. He described it as a mathematical convenience, a clever adjustment to force the equations to behave not a genuine statement about how nature works. He expected future physicists to replace his odd little assumption with something more comfortable, something more classical. What he didn't realize was that he had opened a door that could never be closed again. His simple suggestion that energy comes in discrete packets became the seed of an entirely new framework, a framework that would soon unravel many of the assumptions classical physics had taken as absolute truth. Looking back, it feels like the moment a revolution began, but at the time it was just a quiet paper published without fanfare in 1900. No bold predictions, no dramatic claims, just a constant, a calculation, and a small idea that refused to go away. From that moment onward, physics carried a sense of unfinished business. By the early 1900s, scientists believed they understood light quite well. Maxwell's equations showed that light behaved like a wave, a smooth rippling disturbance in the electromagnetic field. It bent around corners, reflected off surfaces, and produced delicate interference patterns. Everything about it looked like a wave. And after Planck introduced quantized energy, many expected things to settle back into a stable, predictable order. But then came a stubborn little puzzle involving metal surfaces, beams of light, and electrons that refused to behave. It was called the photoelectric effect, and on the surface it seemed simple. Shine light onto a metal plate, and electrons pop out. Light provides energy. Energy frees the electrons straightforward enough. But experiments showed something far stranger. Brighter light didn't necessarily give the electrons more energy. Low frequency light, no matter how intense, sometimes did nothing at all. The entire effect depended not on brightness, but on the color, the frequency of the light. Classical wave theory had no explanation, and once again, physics found itself staring at a contradiction it couldn't ignore. According to classical wave theory, turning up the brightness of a beam of light should have been enough to give electrons more energy. A stronger wave should shake them loose more easily. That was the straightforward expectation, simple, intuitive, and entirely wrong. When scientists performed the actual experiments, the results were baffling. Flooding the metal with brighter and brighter light didn't always free electrons with more energy. Sometimes it didn't free them at all. What turned out to matter wasn't the brightness, but the frequency of the light. Below a certain frequency, even an intense beam did absolutely nothing. The electrons simply didn't budge. But once the light crossed that magical frequency threshold, even a faint, gentle beam had no trouble knocking electrons free. This abrupt cutoff made no sense through the lens of classical physics. It was as if nature had drawn a hard line and refused to behave according to expectations. What began as a small experimental annoyance quickly grew into a deep mystery, one that called for someone willing to think in an entirely new direction. That someone was Albert Einstein. In 1905, a year now remembered as his Annus Mirabilis, Einstein proposed a bold idea to make sense of the photoelectric effect. What if light wasn't only a wave? What if in certain situations it behaved as if it were made of tiny particles, little packets of energy traveling in straight lines? He called these packets quanta of light, a term that would soon evolve into the word photon. Each photon, Einstein suggested, carried a specific amount of energy determined solely by its frequency. If a photon held enough energy, it could liberate an electron from the metal. If it didn't, then no number of photons, no matter how bright the beam, could make up for that missing energy. It was like trying to open a locked door with a pile of keys, none of which fit. Quantity didn't matter, only the right key would work. Einstein's insight built directly on Planck's earlier quantization idea, but it took an enormous step further. Planck had used the energy packets as a mathematical fix. Einstein claimed they were real physical entities. Light didn't just act like it came in chunks, it actually did. This was a radical shift, and not everyone embraced it. Many physicists were deeply attached to the wave description of light, and with good reason. Light behaved like a wave in countless experiments. It bent around obstacles, produced interference, fringes, and rippled through space with elegance. How could it possibly also be a particle? Einstein's answer was simple and unsettling. Light is both, not metaphorically, not conveniently, but fundamentally. It behaves like a wave in some circumstances and as a particle in others. Which aspect you see depends entirely on how you observe it. This wasn't a quirk of our perception. It was a truth about nature itself, a truth that classical physics had never prepared us for. Light existed in a category of its own, refusing to fit neatly into any familiar box. And in that refusal, the foundations of quantum physics began to take shape. Imagine a ray of sunlight slipping through a window pane. From a distance, it behaves exactly as you'd expect a soft wave spreading through the room, rippling across dust particles, brushing gently over glass. But if you could shrink yourself down and look closer, much closer, you'd find something very different happening beneath that warm glow. You'd see countless tiny packets of energy, each with its own frequency, tapping gently against atoms and nudging the world forward, one microscopic interaction at a time. This strange blend of identities, light acting as both a wave and a particle, is one of the most bewildering ideas in physics. Not because it's mathematically difficult, but because it quietly breaks the categories we've used for centuries to make sense of reality. In the everyday world, things are neatly sorted. Objects are solid or fluid, here or there, moving or still. Waves are waves. Particles are particles. They do not switch roles based on mood or circumstance. But the quantum world doesn't bother with our rules. It behaves according to its own logic, whether we understand it or not. Einstein's explanation of the photoelectric effect captured this duality with startling clarity. The energy of each photon depended purely on its frequency, just as Planck had hinted. And that simple fact perfectly explained why low frequency light, no matter how intense, couldn't knock electrons loose. Those photons simply didn't have enough energy in each individual packet to do the job. The weight of this idea was enormous. In 1921, Einstein received the Nobel Prize for this work, not for relativity, but for showing that light sometimes behaves like a stream of particles. That's how groundbreaking the discovery was. Yet even Einstein, brilliant and bold as he was, found himself uneasy as quantum theory grew stranger. He pushed back against interpretations that relied too heavily on randomness or probability. God does not play dice with the universe. He famously insisted a line that revealed just how uncomfortable he was with the emerging quantum picture. But whether the universe played dice or not, the game had begun. The old boundaries were dissolving. Light refused to be one thing or the other. It arrived in quanta. It spread like a wave. It struck like a particle. It shimmered between these descriptions, always hinting at its true nature, yet never offering the complete story. And what started as a simple attempt to understand how light interacts with metal soon shook the entire foundation of physics. Because if light, the thing that fills our days and defines our vision, could defy categorization so effortlessly, what else might be behaving strangely behind the curtain of everyday experience? That question leads us to one of the most quietly astonishing experiments ever devised. No giant machines, no exotic equipment, just a flashlight, a sheet of cardboard, and two narrow slits. You shine a beam of light through those slits and watch how it lands on a screen behind them. It sounds almost disappointingly simple, like a child's science fair project. And yet, this tiny setup hides one of the deepest puzzles in all of physics. The double slit experiment has become legendary, not because it's complicated, but because its simplicity leaves no room to hide from its implications. Some physicists have joked that it's the most dramatic experiment in history, starring the most unglamorous props imaginable, two holes cut into a piece of cardboard. Let's start with what common sense tells us should happen. In the classical world, waves and particles behave in very different ways. Waves, whether in water, sound, or light, spread out and blend together. If you let ocean waves pass through two openings, the water on the other side forms a beautiful pattern of crests and troughs reinforcing each other in some places and canceling out in others. That's interference, and it makes perfect sense. Now imagine firing tiny solid pellets, little rubber balls, at a barrier with two openings. Some balls go through the left slit, some through the right. They scatter and pile up in two neat clusters on the wall behind. No interference, no blending, just simple, predictable behavior. But quantum physics rarely lets us stop at simple and predictable. On the screen behind the slits, the expectation was simple. If light behaved like tiny pellets, you'd see two tidy clusters of marks lined up with the openings clean, predictable, no mystery hiding in the shadows. That would be the particle picture: straight lines, straight answers, nothing to lose sleep over. But when scientists first sent a beam of light through those two narrow slits, it behaved just as classical wave theory predicted. The light fanned out in gentle ripples and painted the screen with a sequence of bright and dim bands, an interference pattern created by overlapping wave peaks and troughs. In that moment, everything seemed perfectly sensible. Maxwell's elegant wave equations were holding up beautifully. Light was a wave. End of story. Except the story didn't end. With more precise instruments, researchers began lowering the intensity of the light source until they were releasing photons one by one, single quanta of light, drifting through the darkness toward the slits like tiny travelers on a quiet road. And here's where intuition completely unraveled. Sending individual photons should have produced two simple clusters of hits. Each photon travels alone. Each photon should choose a path. Over time, they should have produced a particle-like pattern, but they didn't. Even when released singly, with vast time between each photon, the final pattern on the screen slowly grew into the same wave-like interference pattern as before. One photon at a time, the universe seemed to whisper the same impossible story. Each photon was behaving as if it went through both slits simultaneously, interfering with itself, exploring every potential route before choosing a place to land. How could a single particle spread out like a wave? How could it act as though it traveled down two mutually exclusive paths at once? This wasn't a trick of the equipment. It wasn't noise. It was the most repeated, verified, and stubbornly consistent result in quantum physics. Naturally, scientists tried to peek behind the curtain. They placed tiny detectors at the slits to identify which path each photon actually took. It seemed like a harmless question, just a gentle look, nothing more. Surely the photon must have chosen one slit or the other. But the moment they tried to observe its path, everything changed. As soon as the detectors were activated, the interference pattern disappeared completely. The photons stopped behaving like waves and began landing in two neat clusters, exactly as classical particles would. It was as though the act of observing forced the photon to settle down, pick a single route, and behave normally. Turn off the detectors, and the wave pattern returned. Turn them on again, and the wave pattern vanished. The universe oddly enough responded to whether the path was knowable. This didn't happen because the detectors pushed or disturbed the photons. These experiments used extremely delicate, non invasive methods. The shift wasn't caused by the mechanics of measurement, it was triggered by the simple fact that the information could be known. The mere presence of knowledge was enough to collapse the photon's spread of possibilities into one definite outcome. It was as if reality rearranged itself the instant awareness entered the picture, and this bizarre behavior isn't limited to photons. The experiment has been repeated with electrons, neutrons, entire atoms, even molecules composed of hundreds of atoms. Systems far larger than anyone expected quantum effects to matter. Left unobserved, they behave like waves and interfere with themselves. Observed, they fall into the crisp, predictable order of particles. This phenomenon sits at the core of quantum theory, and it resists every attempt to translate it into everyday language. It hints that at the smallest scales, particles don't follow fixed trajectories. Instead, they exist as clouds of possibilities, fluid, probabilistic, unresolved. A measurement doesn't just reveal which option is true, it forces the system to choose. Different interpretations try to make sense of this. Some imagine the particle's wave spreading through both slits and recombining. Others see the wave function as nothing more than a mathematical tool describing probabilities. And some in the many worlds picture every possible path happening in parallel universes. But regardless of interpretation, the experimental facts stand. Until something is measured, the particle remains suspended in a haze of potential. Only when we look does it commit. What started as a simple curiosity about how light behaves quietly unfolded into a far deeper puzzle, one that doesn't just touch physics, but tugs at the edges of reality itself. A pair of slits, a beam of light, and a screen behind them somehow revealed questions that feel almost philosophical. Does observing something actually participate in shaping it? Does information itself have influence? Is the universe somehow undecided until we ask it a question? These aren't abstract thoughts written in poetry. They're grounded in repeated experiments, measured carefully, confirmed again and again. The double slit experiment doesn't hand us a single tidy explanation, but it does whisper one profound insight. The universe, at its most fundamental level, isn't a rigid machine. It's a shifting landscape of probabilities, a shimmering web of potential outcomes that adjusts in strange ways when we turn our attention toward it. When we don't look, it behaves one way. When we do, it straightens, as if acknowledging our presence. From this soft but staggering mystery, we move to the quiet engine that powers the entire quantum world, a piece of mathematics so central that physicists often describe it as the heartbeat beneath everything. Schrodinger's equation. Don't worry, We're not about to dive into chalkboards or dense symbols. In fact, you can stay as relaxed and drowsy as you are. Schrodinger's equation isn't important because of how it looks. It's important because of what it represents. Back in the 1920s, the old rules of physics were beginning to crack. Electrons were behaving like waves, photons were refusing to act like simple particles, and the neat clockwork formulas that had guided physics for centuries were suddenly out of tune with reality. Scientists needed something new, something that could describe objects that acted more like drifting probability clouds than tiny billiard balls. That's when Erwin Schrödinger stepped in. In 1926, he introduced an equation that didn't track particles the way Newton's laws do. Instead, it described how a particle's wave function, its soft, hazy field of possibilities, changes over time. It was an equation that captured motion not as a single path, but as a fluid evolution of chance. Compact, elegant, and astonishingly effective. At the center of this picture is the wave function usually written as the Greek letter psi. You can imagine it almost like a faint, shimmering mist spread across space. Instead of saying the particle is here, it says the particle could be here or there, or somewhere in between, with certain probabilities. Classical physics gives you a clean answer. Quantum physics gives you a gentle cloud. Schrodinger's equation lets that cloud evolve like ripples spreading across a pond. It shows how possibilities drift, overlap, or sharpen. And then when you perform a measurement, when you gently ask the universe, where exactly is this particle? Right now, the entire mist collapses into a single point. It's as if the wave of maybes snaps into a single, quiet yes. This collapse doesn't happen until we look. Until then, motion is possibility. This way of thinking broke completely from the fixed, predictable world of classical mechanics. Rather than tracing perfect orbits or straight line trajectories, quantum objects swim through a fog of potential positions and outcomes. Only our observation pins them into something definite. To make this more visual, imagine standing in a dim room with a blindfold on. Somewhere nearby, a quiet cat is wandering. You can't see it. You can't hear its paws, but you can toss small objects and listen to where they land. Over time, with each tiny sound, you build a mental map of where the cat might be. Not the exact spot, just a distribution of likelihoods. The places it's more likely to sit, the places it rarely goes. That mental map, that soft probabilistic sketch, is what the wave function is. And Schrodinger's equation is the rule book for how that map changes second by second. The actual math is continuous, smooth, almost musical in how it flows. It respects the deep symmetries of nature, energy, motion, time, and yet it refuses to deliver certainty. It gives us patterns, not promises. And the most remarkable part is how precisely it works. Schrodinger's equation explains why atoms hold together instead of collapsing, why electrons occupy specific energy levels, why chemical bonds exist, why semiconductors behave the way they do, why superconductors carry current without resistance, even how particles tunnel through barriers they seemingly shouldn't cross. One of its earliest triumphs was the hydrogen atom, the simplest atom in the universe. Before quantum mechanics, no equation could fully explain why electrons didn't spiral inward toward the nucleus or fly off entirely. Schrodinger's equation changed that overnight. It predicted the allowed energy levels perfectly matching experimental data down to astonishing precision. This wasn't just a new formula, it was a new vision of reality, one where the universe doesn't march forward like gears in a machine, but drifts, ripples, and blossoms with possibility until observation brings a moment of clarity. Schrodinger's equation opened a doorway into a world that looks nothing like the tidy diagrams we once imagined. Electrons aren't tiny planets racing around a miniature sun. They don't trace sharp orbits or follow fixed paths. Instead, they settle into something much softer, stable, standing waves of possibility wrapped around the nucleus like quiet, shimmering halos. These patterns are what we call orbitals, the cloud like shapes you may have seen in textbooks. But those clouds aren't illustrations. They're not guesses or artistic approximations. They are the literal, measurable distribution of where an electron is likely to be found if you choose to observe it. Not orbits, not loops, but presence zones regions where the particle's probability gathers and rests. They exist as only because an electron is not a simple solid bead of matter. It's a ripple in a deeper, invisible sea of potential, a vibration in the mathematics, a wave of maybes. It's a strange idea at first, even unsettling, but it's also unbelievably coherent. Schrodinger's equation doesn't wobble or contradict itself. It doesn't need patches or last minute fixes. It has survived a century of experiments with incredible accuracy, and every time we push into smaller and stranger territories, from atoms in your cup of tea to the microchips inside your phone, it continues to describe the behavior of the quantum world perfectly. Yet, for all its precision, the equation remains hauntingly abstract. You can't hold a wave function in your hand. You can't peer into a microscope and see one glowing. It exists in the mathematics, in the predictions, in the quiet way reality behaves. But despite its invisibility, it describes something undeniably real. Every electron in every atom of your body follows its rhythms. And then comes the question that transforms physics into philosophy. What is the wave function truly? Is it a map of our knowledge, a tool for predicting what we'll find when we look? Or is it an actual piece of the universe, something that exists out there, independent of us, rippling gently until measurement causes it to collapse into a single outcome? Physicists still argue about this, sometimes passionately. Entire interpretations of quantum mechanics branch off from this single question. The mathematics doesn't choose a side, it simply works. Even Schrödinger himself felt uneasy about where his equation led. He gave the world this beautiful, soft vision of particles as waves, then immediately questioned the implications. His thought experiment, the infamous cat both alive and dead, until observed, wasn't meant as a playful paradox. It was his way of saying, surely this can't be the whole story. In a sense, he was rebelling against the very strangeness his work revealed. But despite his doubts, it's hard not to admire what he created. In a universe that often pushes us toward rigid categories, yes or no, here or there, particle or wave, Schrödinger introduced something far more delicate, a mathematical language that doesn't force the world into boxes, but lets it breathe in possibility. His equation doesn't thunder with certainty. It murmurs, it guides, it traces the gentle motion of probability as it flows and shifts. And through that quiet guidance, it reveals a reality much softer, subtler, and more mysterious than any classical picture ever allowed. At the tiniest scales, the world stops behaving in the familiar way we're used to. Motion isn't always motion. Position isn't always position, and certainty becomes more of a luxury than a rule. Yet, even in this haze of possibilities, one elegant idea helps us navigate the strange terrain with a kind of quiet mathematical grace. In the classical world, the world of cars, coffee cups, and anything you can hold in your hand, you can know exactly where something is and exactly how fast it's moving at the same time. There's nothing mysterious about it. A speedometer can just you the velocity of a car, and a GPS can tell you precisely where it is. No conflict, no paradox. But the quantum world doesn't offer the same clarity. In the 1920s, Werner Heisenberg introduced a principle that would become one of the defining features of quantum physics. It was strange, unsettling, and deeply profound. He called it the uncertainty principle, and at its heart is a simple but astonishing statement. The more precisely you know a particle's position, the less precisely you can know its momentum, and the more precisely you know its momentum, the fuzzier its position becomes. Momentum, after all, is just mass times velocity. In everyday life, this idea sounds almost absurd. You can watch a train pulling into a station and know exactly where it is and how fast it's slowing down. There's no tension, no contradiction. But on the quantum scale, reality itself refuses to give up both answers at once. And importantly, this isn't because our tools are clumsy or our technology isn't good enough. The uncertainty isn't a flaw in our measuring devices. It's a fundamental feature of the universe. Even if we invented the most perfect non intrusive probe imaginable, even if we could somehow observe an electron without touching it at all, the uncertainty would still remain. It's woven directly into the mathematics. Part of the reason lies in the wave like nature of particles. Imagine trying to pinpoint a single wave out on the ocean. You can mark the moment when a crest rises in front of you, but the wave itself stretches outward, not confined to a single location. Quantum particles, described by their wave, functions behave in a similar way. They're not dots, they're spreads of possibility. If the wave function is wide and gentle, you lose precision about where the particle is, but you can get a relatively good idea of its momentum. When you squeeze that wave narrow, trying to trap the particle in a tiny region, its momentum becomes wildly uncertain. The wave grows choppy. The more you confine it, the more energetically it pushes back. It's a built in trade off, one the universe never negotiates on. The uncertainties in position and momentum always multiply to at least a tiny constant, Planck's constant divided by 4p. That number is unimaginably small, which is why we don't notice these effects in the macroscopic world. You can measure a baseball's position and speed with exquisite precision and never even brush against the quantum limit. But at the scale of electrons' atoms and the faint architecture beneath reality, the uncertainty principle becomes impossible to ignore. It shapes how electrons occupy orbitals, how atoms bond, how particles behave inside stars, and even how the semiconductor chips in our phones function. And if you try to confine a particle too tightly, locking it into a tiny box, it begins acting restlessly, almost defiantly. Its momentum spreads out. Its energy rises. It refuses to sit still. It's as if the quantum world won't let you pin anything down without a cost. This is the subtle beauty of Heisenberg's principle. It tells us that nature is not built from rigid mechanical pieces, but from ripples and probabilities. It reminds us that even in the smallest corners of existence, certainty is something the universe gives only sparingly. And somehow that lack of sharp edges makes the quantum world feel calmer, softer, and strangely more alive. Try to pin it down further, and it resists even more, as though nature itself doesn't like being told exactly where anything belongs. This isn't a flaw in our machinery or a mistake in our calculations. It's a blur that can't be wiped away, a softness built into the structure of reality. One way to imagine it is like trying to hold mist in your hands. The tighter you squeeze, the less you have. But open your hands just a little, and more of it lingers. That's the delicate balance between knowing too much and being forced to let go of something else. In its own quiet way, the uncertainty principle becomes a philosophical warning label attached to the quantum world. It tells us that knowledge has boundaries, not because humans haven't built good enough tools, but because this is simply how nature works at its most fundamental level. We're not dealing with tiny billiard balls rolling neatly across a table. We're dealing with waves of probability, with shimmering possibilities, with things that refuse to be nailed down too tightly. And this principle doesn't only shape what we can measure, it shapes the universe itself. It explains, for instance, one of the most basic facts of existence: atoms don't collapse. If you've ever wondered why electrons don't simply fall into the nucleus, since opposite charges attract, that answer lies here. If an electron were to collapse inward and stay exactly at the nucleus, its position would be perfectly known, and that would force its momentum to become infinitely uncertain. Infinite uncertainty means infinite energy, and nature simply doesn't allow that. So electrons hover not because they choose to, but because the quantum rules won't let them do anything else. The uncertainty principle creates a built in resistance to absolute confinement, a gentle pushback from the universe against the idea of perfect precision. And this strange limit shows up in other pairs of quantities too: energy and time, angular momentum and orientation. Increase precision in one, and the other slips further out of reach. It's a universal truth at the quantum level, and surprisingly, there's something comforting in it. This uncertainty isn't chaos. It isn't randomness spiraling out of control. It's a structured ambiguity, a graceful fuzziness that gives the universe its texture. It allows particles to tunnel through barriers. It lets atoms stay stable. It makes chemistry possible and life eventually inevitable. Without it, the universe would be far too rigid to support the complexity we rely on. Much of science has always been about finding certainty, pinning things down, predicting outcomes, knowing the rules. Heisenberg's insight gently turned that desire back toward humility. He showed that some truths will always remain just out of reach, and that this isn't a failure. It's simply reality wearing its true form. In a way, the uncertainty principle invites us to relax our grip on certainty, to sit quietly with the blur and appreciate the softness beneath the surface. It reminds us that some of the deepest truths aren't sharp edged at all. They're cloudy, rippling, and unresolved, and perhaps that's why they feel so strangely beautiful. In our everyday world, everything seems to commit to a single state. A coin lands heads or tails. A light switch is on or off. Your tea is hot or cold, though sometimes questionably lukewarm. But in the quantum world, this tidy division collapses. Objects at the smallest scales don't always pick a side. They can rest in an in between state, a blend of all possible outcomes at once. This is the realm of quantum superposition. To picture it, imagine flipping a coin. In the classical world, once it leaves your hand, it's already determined it will be heads or tails long before you catch it. You simply don't know at which until you look. In the quantum world, though, a coin in midair doesn't secretly land on one side while you're not watching. Instead, it enters a state where it is genuinely both a weighted combination of heads and tails at the same time. It isn't indecisive, it isn't flickering rapidly between the two. It is physically in a superposed state, a quiet blend of possibilities until the moment you observe it. And when you finally look, the superposition collapses. The quantum coin chooses a face. Your measurement becomes a single outcome. Before you looked, it wasn't just unknown, it was both. And that idea is not just counterintuitive, it's profoundly, deliciously strange. Superposition was first introduced as a way to describe the behavior of quantum particles like electrons and photons. These particles, instead of following clean and predictable paths, exist as wave functions, mathematical expressions that describe probabilities rather than certainties. Each possible state, whether a spin pointing up or down a photon, going left or right, an electron appearing here or there, is woven into that wave function. All of those possibilities coexist quietly, like sheets of fog overlapping in a valley, until a measurement is made and one outcome becomes real. You can imagine it like standing in a landscape covered in mist. The particle isn't choosing a single path, it's smeared across every possible route it could take. And the moment you interact with it, the fog suddenly snaps into a single, clear hilltop, illuminated for just an instant by a flash of lightning. This idea eventually led to one of the most famous thought experiments in all of physics, Schrodinger's cat. Picture a cat inside a sealed box with a tiny radioactive atom, a detector, and a vial of poison. If the atom decays, the detector triggers the vial to break and the cat dies. If the atom does not decay, the cat lives. According to quantum mechanics, until someone observes the atom, it exists in a superposition of both decayed and not decayed. And so, by extension, The cat is both alive and dead until the box is opened. Schrödinger didn't intend this to be taken literally. He designed it to show how absurd it is to stretch quantum rules into the everyday world. But the image stayed with us. It gave superposition a form that was impossible to ignore, a reminder that the quantum world plays by rules that feel deeply strange when brought into the familiar scale of cats and boxes. And yet, despite how weird it sounds, superposition is not a glitch or an awkward loophole. It's one of the most powerful and essential features of quantum mechanics. In fact, much of modern quantum technology depends on it. Consider quantum computing. In a classical computer, the smallest unit of information is the bit, which can be either 0 or 1. Everything your phone or laptop does, every photo message and calculation, is built from combinations of these two states. Quantum computers instead use qubits, and a qubit, unlike a classical bit, can exist in a superposition of 0 and 1 at the same time. It's not flipping rapidly between the two. It is genuinely in a blended state of both. A single qubit can hold far more information than an ordinary bit, and when multiple qubits become entangled, the amount of information they can represent grows explosively, allowing quantum computers to solve certain kinds of problems that classical computers struggle with. Complex simulations, molecular behavior optimization, challenges. They all become far more manageable when you let information live in superposition. It isn't magic, it's simply mathematics operating under quantum rules. Superposition also plays a role in quantum cryptography, helping ensure that information can't be intercepted without leaving a trace. In quantum sensing, it allows scientists to detect ultra small changes in magnetic or gravitational fields with extraordinary precision. These aren't speculative ideas, they're emerging technologies being built and tested right now. But there's a catch. Superposition is fragile. Quantum systems are easily disturbed. A stray photon, a vibration, a molecule of air brushing against the system. Any tiny interaction with the environment can collapse the wave function. This process is called decoherence, and it's one of the biggest challenges in developing real stable quantum technologies. It's like trying to balance a feather on the tip of a pencil while someone in the next room is quietly sneezing. The slightest disturbance breaks the delicate state. Superposition lets the quantum world glow with possibility, but holding those possibilities in place long enough to use them is a challenge that researchers are still learning how to overcome. The superposition vanishes the moment the system touches the outside world, and that fragility is part of what makes quantum systems so endlessly fascinating. They carry immense potential, but only when they're sheltered from noise, vibration, heat, or even the faintest whisper of interference. They offer us probability instead of certainty, possibility instead of fixed truth, and they quietly invite us to rethink what it really means to say that something exists at all. And woven into this is a deeper philosophical question, one that physicists have been debating for a century. When a particle exists in multiple states, is that a reflection of the particle itself, or a reflection of our knowledge of it? Some interpretations suggest the wave function is simply information a map of what we can say about a system until we finally look. Others argue that the wave function is real and the particle genuinely occupies multiple states at once until observation pins it down. Either way, quantum superposition asks us to loosen our grip on classical logic. It suggests that opposites can coexist, that something can be here and there, this and that, yes and no, all at the same time. At the smallest scales, reality isn't a single clean thread. It's a woven tapestry of overlapping possibilities unresolved until our observation pulls one strand loose. It's strange, unsettling, and profoundly counterintuitive, but there's a kind of delicate beauty in it too. Because hidden inside this rule of superposition is a universe that isn't rigid, but flexible, not mechanical, but quietly poetic. It's a universe that allows contradiction without breaking, that embraces uncertainty as part of its structure, not a flaw. And by accepting that we open up entirely new ways to compute, to communicate, to measure, and to imagine what might be possible when reality itself hesitates before choosing a single outcome. Now imagine something even stranger. Imagine you have two gloves, one left handed, one right handed. You seal each one inside its own box and send one halfway across the world. Before you open either box, you don't know which glove is where, but the instant you open the first box and see a left glove, you immediately know the distant box holds the right glove. There's nothing mysterious about that. The gloves were always what they were. Your uncertainty was only ignorance. Quantum entanglement is nothing like this. Entangled particles aren't preassigned like gloves. Instead, they behave like a pair of gloves that haven't decided which hand they belong to until the moment you open a box, and once you do, the other glove instantly adopts the opposite orientation, no matter how far away it may be. It's not simply that the outcomes are correlated, it's that the properties themselves don't seem to exist until the moment one of them is measured. And somehow, mysteriously and instantly, the act of measuring one appears to determine the state of the other. This is quantum entanglement, one of the most bewildering and deeply unsettling features of the quantum world. Here's the essence of it. When two particles interact in just the right way, when they're created together, collide, or otherwise become deeply connected, their quantum states become intertwined. They stop being two separate systems and instead become one shared state stretched across space. Whatever happens to one affects the other even across enormous distances. Imagine creating two entangled photons with uncertain polarizations. Neither photon has a definite orientation until someone measures it. One might collapse into a vertical polarization and the other into a horizontal one, but neither decides until the first measurement is made. And somehow the second photon, even if it's on another continent or on a spacecraft drifting beyond the moon, instantly adopts the complementary state. Einstein famously called this spooky action at a distance a phrase that captured both his disbelief and the strangeness of the phenomenon. He suspected the quantum theory was incomplete, that there must be hidden variables deciding the outcomes ahead of time, like gloves tucked secretly into boxes. But decades of experiments showed otherwise. The universe doesn't behave like hidden gloves. The correlations between entangled particles are stronger than any classical system can allow. They violate the very limits that hidden variables would obey. Entanglement is real, it's measurable, and it's woven into the structure of the quantum world. But the strange part is this: the particles don't secretly decide ahead of time who gets which outcome. They don't carry hidden instructions or pre written identities. Instead, they remain in a single, shared quantum state, a superposition of all possibilities, until the very moment you measure one of them. And when that moment arrives, when one particle finally commits to an outcome, the other locks into a complementary state instantly. No signal travels between them. No information crosses the space. There's no delay, no whisper, no opportunity for communication. If you measure one photon in Paris and its entangled partner is drifting somewhere above Tokyo, the second photon's state becomes definite in the same instant, as though the universe quietly updated both sides at once. This is the phenomenon that Einstein famously described as spooky action at a distance. And Einstein, despite his love for the mysterious beauty of physics, was not fond of anything spooky. His worldview was rooted in locality, the principle that physical effects must occur through contact or signals that travel no faster than light. Relativity depends on this idea. Causality depends on it. The notion that two far separated particles could coordinate perfectly without exchanging any signal at all made him deeply uneasy. In 1935, Einstein, alongside Boris Podolsky and Nathan Rosen, published the famous EPR paper challenging the completeness of quantum mechanics. Their argument was straightforward. If quantum mechanics allows such instantaneous correlations, then it must be leaving something out. There must be hidden variables, undiscovered mechanisms, quietly determining outcomes behind the scenes. To Einstein, the universe should be predictable, orderly, and local. The quantum picture seemed too dreamlike, too loose, too willing to let go of realism. But decades passed, and quantum mechanics kept holding up. In the 1960s, physicist John Bell devised a brilliant mathematical test, a way to distinguish whether the universe truly obeyed hidden variables or whether it behaved the way quantum mechanics predicted. These tests, now known collectively as Bell experiments, were performed again and again in laboratories around the world. And every time the universe answered the same way, entanglement is real. Local hidden variables simply don't describe the world we live in. The correlations posed between entangled particles are stronger than any classical system can produce. They follow no predetermined script. The outcomes are individually random, yet somehow perfectly coordinated, like two actors improvising the same scene in perfect harmony without ever rehearsing or communicating. Still, this strange connection doesn't allow us to cheat physics. You cannot use entanglement to send messages faster than light. Nature protects causality in its own subtle way. Even though entangled particles respond to each other instantly, the results of each measurement are fundamentally random. You can't choose what outcome you get, so you can't encode information into it. It's like two people on opposite sides of the galaxy flipping coins. Each flip is random, But somehow, when one sees heads, the other sees tails. There's no message being sent, just a mysterious synchronization that transcends distance. What makes this even more astonishing is that the connection doesn't fade with space. You could separate entangled particles by the width of a room, a continent, or a light year, and the entanglement would endure. There's no known distance limit. Physicists have even entangled particles using satellites spanning hundreds of kilometers through the vacuum of space, and the quantum correlations remain perfectly intact. Whatever entanglement is, it's not fragile in the way ordinary connections are. It doesn't stretch, it doesn't weaken, it doesn't lag behind. But what exactly is it? Is entanglement an invisible thread tying two particles together? Is it a shared identity smeared across space? Is it a kind of quantum information that doesn't live in either particle but in the relationship between them? Or is it something even deeper? Evidence that reality itself is not local, not separate, not chopped into independent pieces the way we instinctively assume. The truth is that no one fully knows. Different interpretations of quantum mechanics paint different pictures. Some say entanglement reflects only what we can know, not what exists. Others argue it reveals the true fabric of the universe, a reality where separation is illusion, where distance is secondary, where connection is more fundamental than space. There's even a growing line of thought, one that has quietly gained momentum in modern physics, that entanglement might not just be a strange quantum behavior, but something far more profound. Some researchers have proposed that space-time itself, the very fabric of the universe, may arise from vast networks of entanglement woven between countless tiny quantum bits. If that idea is correct, then entanglement isn't something that happens inside space. It's the subtle stitching that creates space, the invisible framework that holds the entire geometry of the universe together. It's a bold and still speculative idea, but it hints at how central entanglement may be not just for particles, but for the deep architecture of reality. And like many mysteries in quantum physics, it doesn't stay confined to theory. Entanglement has practical uses, real, tangible applications that scientists work with today. It forms the basis of quantum teleportation, not the science fiction version of transporting people across galaxies, but a very real process of transferring the state of one quantum system to another without physically moving the particle itself. It also powers quantum key distribution, a new form of secure communication where the safety of the message is guaranteed by the laws of physics. If anyone tries to eavesdrop, the entanglement is disturbed and the intrusion becomes instantly detectable. In quantum computing, entanglement is what allows multiple qubits to behave not as isolated units, but as members of a vast interconnected whole. It gives quantum processors their extraordinary potential and ability to explore countless possibilities simultaneously in ways classical computers simply cannot. What once seemed like a source of deep discomfort, even to Einstein, has become a foundational tool in cutting edge technology. Relativity may govern the cosmic scale, and quantum mechanics, the microscopic one. And though we still haven't unified these two great pillars of physics, both have proven remarkably accurate in their own domains. Entanglement reminds us that the universe is not just a collection of isolated objects moving independently. At a deeper level, it behaves like an intricate web of relationships, where even distant particles can act as parts of a shared whole. It's a kind of quiet togetherness woven into the smallest scales of nature, something we never see in daily life. You don't find yourself entangled with your neighbor or discover your morning coffee changing because someone across the planet that moved a spoon. But beneath the surface, this subtle connection between particles is happening constantly everywhere all the time. And maybe that's the most surprising part, that in a universe filled with enormous distances, empty space, and long stretches of silence, there are still traces of something intimately connected. Tiny echoes of partnership that stretch across the void, instant and invisible, yet undeniably real. Among all the strange creatures in science, few are more iconic than Schrodinger's cat. This imaginary cat has become a symbol of quantum physics itself, a reluctant mascot trapped inside a thought experiment that's so peculiar it almost sounds like a parody. And in a sense, it was meant to. Schrödinger didn't intend the cat to be taken literally. He designed the scenario as a way of exposing just how unsettling the implications of quantum theory can be. The idea took shape in the 1930s, at a time when physicists were struggling not with the equations they worked beautifully, but with the meaning behind them. What was quantum mechanics actually telling us? Was the wave function describing something real? Were particles truly existing in multiple states at the same time until observed, or was the wave of function nothing more than a mathematical tool for predicting outcomes? Erwin Schrödinger, already known for the graceful equation that bears his name, was growing increasingly uneasy with how confidently some physicists were stretching the idea of superposition. He wasn't troubled by the mathematics itself, those worked flawlessly. What unsettled him was the way certain interpretations seemed to imply that quantum rules applied just as well to ordinary everyday objects as they did to electrons and atoms. That leap felt suspicious to him, almost reckless. So he offered a challenge, a deliberately playful but undeniably dark scenario meant to expose the tension in the theory. His thought experiment began with a simple question: what happens if you take the strangeness of quantum mechanics and scale it up to something familiar, something you could pet feed or hold in your arms? Picture a closed box. Inside it sits a cat, perfectly ordinary, perfectly alive. Also inside the box is a single radioactive atom, a Geiger counter, a small vial of poison, and a mechanism designed to break the vial if the atom decays. The decay of a radioactive atom is a fundamentally quantum event. It's unpredictable, governed entirely by probability. It may decay in the next second, or it may not. According to quantum mechanics, until we observe the atom, it exists in a superposition of both decayed and not decayed states. And here's the unsettling consequence. If the atom is in a superposition, then everything connected to it should be as well: the detector, the trigger, the vial, and yes, the cat. By the logic of the theory, the entire system becomes a blend of outcomes. The cat is simultaneously alive and dead, not metaphorically. Literally, if you follow the mathematics strictly. Schrödinger never intended anyone to build such a box. His point wasn't cruelty, it was clarity. He wanted to highlight how absurd it sounded to apply quantum rules that work beautifully for subatomic particles to something as warm and familiar as a living creature. To him, the idea that a cat could spend any meaningful amount of time in a state that is neither alive nor dead was not just strange, it was nonsensical. And yet the thought experiment survived, not because anyone believed a cat could be both alive and dead, but because it captured the heart of the quantum dilemma in a single, unforgettable image. Until we look, quantum systems are described by a haze of possibilities. When we observe them, that haze collapses into a single outcome. The cat in the box story takes that principle and stretches it until the weirdness becomes impossible to ignore. It forces us to confront an uncomfortable question. What does it really mean to observe something is a measurement, something that requires a conscious mind? Or is it simply an interaction, any interaction that leaves a trace in the environment? Does a photon bouncing off an object count as a measurement? Does a detector with no human nearby count? Does a vibration, a heat exchange, even the tiniest whisper of contact with the outside world count? The truth is, no one fully agrees. The quantum formalism tells us how systems evolve and how they collapse, but not precisely where the boundary lies. Some interpretations suggest there is no boundary at all, that the world is always quantum, all the way up. Others insist that something special happens when information becomes irreversibly recorded or when consciousness enters the picture. Schrödinger's cat endures because it sits exactly at that crossroads. It exposes a deep ambiguity that still hasn't been resolved. It reminds us that quantum mechanics, for all its power and precision, still leaves us with questions about what reality is doing when no one is watching. Different interpretations of quantum mechanics give different answers, and that uncertainty is part of the reason Schrödinger's imaginary cat still appears in so many conversations. The cat forces us to acknowledge something uncomfortable. Quantum theory, despite its remarkable accuracy, says very little about what's actually happening between measurements. It can tell us the odds, the patterns, the statistics. But the story behind the scenes, the why and the how, remains oddly blank. Some physicists lean into the Copenhagen interpretation, the oldest and perhaps simplest. The wave function is a tool for predicting outcomes, not a literal blueprint of reality. In that view, asking what the system is doing before you measure it is the wrong kind of question. You measure, the system resolves, and that's that. Don't look for hidden details that the theory never promised to give. Others find that unsatisfying and prefer the many worlds interpretation. In that version of events, the cat isn't in a vague limbo. Instead, the universe itself branches. In one branch, the cat survives. In another, it doesn't. Both outcomes are fully real, just no longer in the same timeline. Opening the box doesn't force a decision, it simply reveals which branch you happen to occupy. Then there's decoherence, a more modern approach. Decoherence suggests that the moment a quantum system becomes entangled with its environment. Air molecules heat photons. Anything the delicate superposition effectively dissolves. Not because the possibilities vanish, but because they spread into the surroundings so thoroughly that we can no longer track them. In this interpretation, the cat isn't hovering in an impossible in between. Its state is simply buried under an avalanche of interactions. Each viewpoint comes with its own philosophical weight. Each one tries to answer the same underlying puzzle. Why do quantum rules look so exotic at tiny scales yet appear so ordinary in the macroscopic world we move through? What they all agree on is that quantum systems evolve in ways that do not resemble miniature classical objects. They don't follow a single predetermined path. They drift through clouds of possibilities, shifting and adjusting as probabilities evolve. Which brings us back to the cat. The box in Schrodinger's story is not just a container, it's a symbolic boundary, an imagined border between the quantum and classical worlds. Inside the box, the quantum rules unfold freely. Outside, we expect definite answers. The moment we open the lid, that boundary disappears and the ambiguity collapses into a single result: alive or not. This is why the cat remains such a powerful metaphor. It reminds us that before measurement, quantum systems aren't choosing a path, they're exploring all the paths the mathematics allows. An electron doesn't march from point A to point B like a tiny planet. It spreads across every route, every possibility, until something forces it to declare its position. Schrodinger's cat simply scales that logic upward, and the scale is precisely what bothered him. Because if quantum rules apply universally, then in principle, everything, including us, might be part of some vast superposition until the moment of observation pins things down. And that leads to an even stranger question, the one Schrödinger deliberately left hanging in the air. What if the observer is just another part of the system? If opening the box collapses the cat's wave function, then what collapses ours? Are we just another link in a long chain of measurements? Each observer collapsing the previous one's uncertainty, or is the entire universe evolving in one unbroken, entangled wave, where observation is just an emergent effect? In the end, Schrodinger's cat has very little to do with life or death. It's about the nature of knowledge. It's about how observation interacts with potential. It's about whether reality has a definite state when no one is looking, or whether definiteness only emerges when we ask a question. It reminds us that in the quantum world, certainty is rare and clarity depends on context. Sometimes the universe really does seem to wait for us to lift the lid. And with that lingering thought, we return from the shadowy interior of the box to the comforting world of classical intuition, the realm where tennis balls behave exactly as we expect. If you throw a ball at a wall and it doesn't have enough energy to pass through it, bounces back. Simple, predictable. The universe politely declines your request, and the ball obliges by obeying the familiar rules of everyday physics. But in the quantum world, predictability takes a brief vacation. Down here, the rules soften, blur, and bend in ways that feel almost mischievous. A particle can drift toward a barrier, lack the energy to climb over it, and still somehow materialize on the other side. No cracking through, no burrowing, no forcing its way past. It simply appears there, as though the wall wasn't quite as absolute as we assumed. This peculiar behavior is known as quantum tunneling, and it's one of the clearest reminders that the microscopic world follows a logic entirely its own. It sounds like a glitch, something reality shouldn't allow, but tunneling isn't an error. It's something we can measure, calculate, and rely on. And at its core, it emerges from the probabilistic nature of the quantum wave function. To understand tunneling, we need to revisit that idea. In quantum mechanics, particles aren't tiny pellets scooting along fixed paths. They're described by wave functions, mathematical shapes that spread across space, representing the chances of where a particle might be found. These waves don't stop abruptly at boundaries. They fade gradually, like sound passing through a wall or ripples running out of steam across a pond. So imagine a particle moving toward a region where the energy is higher than what it carries. In everyday physics, that barrier is a firm no entry. The particle just bounces back. But in the quantum picture, the wave function doesn't slam into the wall, it leaks into it slightly. And if the barrier is thin enough, that faint part of the wave can continue to the far side. If any portion of the wave exists beyond the wall, there's a non-zero chance the particle will show up there too. It's not sorcery, it's simply how probability behaves at tiny scales. And although this seems abstract, tunneling has incredibly real consequences. Consider radioactive decay. Inside unstable nuclei, alpha particles, bundles of two protons and two neutrons, sit trapped behind a powerful nuclear boundary. Classically, they don't have enough energy to escape. They should stay locked inside forever. Yet they don't. They escape all the time. Quantum tunneling explains why. The alpha particle's wave function brushes against the edge of the nuclear barrier. Every moment, there is a small chance, tiny, but never zero, that the particle will tunnel through. Given enough time, that chance becomes reality and the particle flies out. Without this process, radioactive decay simply wouldn't happen, and tunneling doesn't stop there. It's also essential for the engine that powers the universe, nuclear fusion. Deep inside, stars' hydrogen nuclei are pushed together under staggering pressure and temperature. But even with that intense environment, the positively charged nuclei still repel each other too strongly for classical physics to allow fusion. They should bounce apart. They shouldn't get close enough to merge. Yet stars shine. Clearly, something lets them fuse in any way. Quantum tunneling is the hidden assistant. It allows these positively charged particles to get close enough despite not having the classical energy required to slip through the barrier and bind. Without tunneling, the sun wouldn't burn, stars wouldn't shine, and the universe would be a much darker place. According to the predictions of classical physics, fusion inside stars should be incredibly rare, far too rare to keep a star burning steadily for billions of years. And yet, stars shine with extraordinary consistency. The reason is tunneling. In the extreme heat of a stellar core, hydrogen nuclei are pushed close enough that their wave functions overlap. In that overlap, There's a small probability, barely more than a whisper, that one nucleus will tunnel through the repulsive barrier and fuse with its neighbor. That chance is tiny on its own, but when you multiply it by the unimaginable number of nuclei inside a star, you get a continuous blazing fusion engine. It's the quiet mechanism behind everything from the warmth of sunlight to the violence of supernovas. And tunneling isn't just a cosmic trick reserved for stars. We rely on it here on Earth, in research labs, manufacturing, and even in the early stages of quantum computing. One of the most beautiful examples is the Scanning Tunneling Microscope, or STM. This tool lets scientists see and map surfaces at the scale of single atoms. It works by bringing an incredibly sharp, metallic tip extremely close to a surface, just a few nanometers away. At that tiny gap, electrons can tunnel between the tip and the material. By measuring that faint tunneling current, the STM constructs an astonishingly detailed image of the atomic landscape. What makes it remarkable is that the microscope never physically touches the surface. It relies entirely on the ability of electrons to quietly seep across a gap that classical physics says should be uncrossable. This kind of non contact imaging becomes a window into the quantum world itself. Tunneling also plays a role in specialized electronic components, such as tunnel diodes and quantum dots. And as engineers push transistors smaller and smaller, tunneling is becoming a major factor in the design of future computers. Once you shrink a barrier to the scale of just a few atoms, electrons begin slipping through places that were once solid and dependable. In modern circuits that can create noise and unwanted behavior. But in the realm of quantum technologies, tunneling is part of the design and asset rather than a problem. At its heart, tunneling teaches us something subtle about the structure of reality. We often imagine boundaries as rigid lines. A particle can go here, but not there. A wall is solid. A barrier is firm. But quantum physics shows us that these boundaries are softer, more like regions of probability than locked doors. They suggest rather than forbid. And what feels like a violation of logic is simply the universe revealing its more flexible side. A tennis ball thrown against a wall always bounces back. But an electron, an alpha particle, a photon, these tiny travelers sometimes encounter the same wall and slip straight through, as if the barrier were more story than substance. Nature doesn't just allow this, it uses it. And that brings us to another deeply strange idea, the quantum vacuum. In everyday life, nothing simply means emptiness, a bare tabletop, an unused corner, the quiet air in an empty room. Stretch that idea into space, and it's easy to imagine the vacuum as a perfect void, cold, dark, silent. But in quantum physics, emptiness is never truly empty. The vacuum isn't a blank canvas. It's a restless and shimmering stage where the background is alive with activity. Even when every particle is removed and every field is supposedly quiet, space still retains energy. At the tiniest scales, the vacuum is full of fluctuations, waves rising and falling, fields flickering, and pairs of particles briefly appearing, then vanishing again. It's like the faint hum beneath silence, a glow that persists even when all lights are off. And all of it arises from a simple principle: uncertainty woven into the fabric of space itself. Heisenberg's uncertainty principle doesn't stop at position and momentum. It extends into energy and time as well. And that extension carries a surprising consequence, even in a region of space where the energy should be exactly zero. Quantum rules allow it to fluctuate for a brief moment. Those tiny fluctuations give rise to what physicists call virtual particles, short lived excitations that appear out of nowhere, linger for an instant, and then dissolve back into the vacuum as if they were never there at all. They aren't virtual because they're imaginary. They're virtual because they can't be observed directly. We only notice them through the subtle fingerprints they leave behind. For something so fleeting, these quantum flickers end up shaping reality in ways that are anything but trivial. One of the clearest demonstrations is known as the Casimir effect, a rare situation where the restless vacuum reveals its presence in a directly measurable way. Imagine placing two ultra thin metal plates almost impossibly close together, just a few nanometers apart, in an otherwise perfect vacuum. Classical physics would predict nothing of interest: no air, no light, no forces acting between them, just emptiness. But the quantum vacuum doesn't behave like a silent void. Because the plates sit so close, only certain wavelengths of virtual particles can exist in that tiny space, those that fit neatly between the boundaries. Outside the plates, though, every allowed wavelength is free to flourish. That mismatch creates an imbalance, slightly more pressure from virtual particles on the outside than on the inside, and that tiny difference pushes the plates toward one another. It's a minuscule force, but it's been measured with exquisite precision. The plates really do drift inward, nudged by what we would usually call nothing. The Casimir effect is a quiet reminder that the vacuum is never truly empty, and that even the most silent regions of space possess structure and energy. On cosmic scales, this vacuum energy has even stranger implications. In cosmology, there's the idea that the energy of empty space may be responsible for the accelerating expansion of the universe. We call that elusive phenomenon dark energy. And while we don't yet know its exact nature, the concept of a vacuum bubbling with fluctuations may hold one of the keys. The complication is that if we try to calculate the vacuum's energy using quantum field theory alone, the result is absurd, roughly 120 orders of magnitude larger than what we observe in reality. It's one of the great unresolved puzzles in physics, a staggering mismatch sometimes described as the worst theoretical prediction ever made. Still, even with its mysteries, the quantum vacuum remains central to how matter behaves. At the microscopic scale, virtual particles mediate interactions in subtle but measurable ways. In quantum electrodynamics, the electric force between charged particles is partly explained by the constant exchange of virtual photons. These brief exchanges shape the strength of electromagnetic interactions. Inside protons, virtual quarks and gluons flicker into existence and alter the proton's mass. Even the stability of electrons in atoms is slightly adjusted by the vacuum's restless background. These fluctuations aren't just theoretical conveniences. Their effects show up in precise measurements, like the famous Lamb shift in hydrogen, where the energy levels of the electron don't match what classical equations predict unless vacuum fluctuations are included. When quantum corrections are added, the calculations line up with experiment to astonishing accuracy. The math is complicated, the imagery is strange, but the results are unshakable. In a sense, the quantum vacuum is the stage beneath every other field in nature. Electromagnetism, gravity, the nuclear forces, all of them operate within this fluctuating background. The vacuum isn't an absence, it's the foundation quietly shaping the behavior of everything that exists. They ripple and shimmer against that underlying vacuum, the way instruments drift over a quiet, steady bass note that never truly stops. Some physicists even wonder whether this restless background holds clues to deeper layers of reality. Could the vacuum be the origin of the universe's structure? Might it contain the seeds of quantum gravity or hints about how space time itself emerges? These questions remain open, but one thing is certain: the vacuum is not a silent stage. It's active, it's textured, it's charged with possibility. Even in the coldest pockets of interstellar space regions, where matter is scarce and starlight barely reaches the quantum vacuum, continues its subtle motion. It flickers, vibrates, and quietly imprints the rules of physics on anything interacting with it. It's humbling to realize that nothing is never truly empty, that beneath every moment of stillness, the universe is quietly at work. Between particles, between heartbeats, between distant suns, something is always unfolding. We're not standing on a motionless platform. We're living on a stage that trembles softly beneath us, a stage whose hidden activity our senses can't detect, but our equations can. The vacuum murmurs. Particles flare in and out of existence, and the fabric of reality moves to a rhythm we've only just begun to recognize. In this quantum landscape, events don't follow the shady narrative arcs we're used to. Particles refuse to trace simple paths. Instead, they drift as clouds of probability. They overlap and tangle tunnel and shift in ways that challenge our everyday instincts. But one of the strangest twists appears when we ask a deceptively simple question: what happens when we look? The act of observation, measuring, detecting, checking seems to trigger something dramatic. It changes the very description of the quantum system. This process is known as wave function collapse. Before you make a measurement, a particle such as an electron exists as a wave function, a mathematical object that encodes every possible state it could occupy. In that form, the electron isn't in one place. It's spread across many. Its spin isn't up or down. It's both. Its path isn't fixed. It's a superposition of every route it might take. The wave function is like a mist of possibilities, drifting through space without committing to any one outcome. But the moment you measure it, when you activate a detector, when you ask the system a question, the wave function collapses. That fog of possibilities condenses into one definite answer. The electron appears in a single location. Its spin takes a definite value. Its many potential paths reduce, to the one that becomes real. And this collapse isn't gradual, it's abrupt, a sudden snap from many possibilities to one, as if the universe, after holding open all its options, chooses a single version of events the moment we ask for clarity. What makes this even stranger is that no one truly knows what triggers the collapse. Is it the physical impact of a measuring device? The moment information becomes available, the role of consciousness, a camera sensor, or is it simply any interaction with the surrounding environment? Even something as subtle as a stray photon brushing past the system, despite collapse being central to quantum mechanics, its exact cause remains one of the deepest puzzles in modern physics. Different interpretations attempt to explain it. The traditional Copenhagen view, championed by Niels Bohr and Werner Heisenberg, treats the wave function as a tool, an elegant way to compute probabilities. In this interpretation, the wave function doesn't represent a physical object. It reflects what we can know. And collapse happens when information is extracted, when we perform a measurement that forces the universe into a single answer. Before the measurement happens, asking where the electron really is simply doesn't mean anything. It isn't hiding in a secret location waiting to be discovered. It isn't in a place at all, not until we look. That's the essence of the Copenhagen view. It's practical, it fits the math beautifully, but it leaves a lingering discomfort because it doesn't truly explain what a measurement is or why the wave function must collapse in the first place. And so other perspectives emerged. One of the boldest is the many worlds interpretation, which discards the concept of collapse altogether. In this view, the wave function evolves smoothly, continuously. It never snaps from many possibilities to one. Instead, every possible outcome becomes real, each unfolding in its own branch of the universe. Measure the spin of an electron, and reality doesn't choose its splits. In one branch, you observe spin up, in another, spin down. You only ever experience one version, but the others continue just as real, traveling their own timelines. No collapse, no special role for observation, just an endlessly branching multiverse, elegant in its consistency, dizzying in its scale. For some physicists, that elegance is irresistible. For others, the idea of a universe multiplying itself endlessly feels excessive, as if we've traded one mystery for an avalanche of worlds. Then there are the objective collapse theories, which take a different approach. They treat the wave function as something physically real, something that can collapse entirely on its own. No observer needed, no measurement required. The collapse happens spontaneously, rarely for small systems, more frequently for large ones. These theories propose new physical laws in an attempt to draw a clean line between the quantum and classical worlds. They're still being tested, but they offer a fascinating possibility. Perhaps collapse is woven into nature itself, not just into our equations. Other views focus less on the external world and more on what we can know about it. One such idea, called cubism, treats the wave function not as a description of reality, but as a reflection of our beliefs about a system. When the wave function collapses, nothing physical changes. What changes is us, our information, our expectations. For some, this brings clarity. For others, it feels too subjective, as if physics drifts uncomfortably close to psychology. And then we have decoherence, a bridge between the quantum and classical worlds. Decoherence doesn't explain collapse directly, but it shows why we never see superpositions in our everyday lives. A quantum system interacting with its environment. Even a few stray particles of light is gently pulled apart by entanglement. Its delicate interference fades. To us, it looks as though the system has chosen a single outcome. But in truth, decoherence doesn't select anything. It simply hides the quantum possibilities behind an overwhelming tangle of interactions. Which leaves us here more than a century after quantum mechanics began reshaping physics with a theory that predicts outcomes stunningly well, yet still whispers a deep, unanswered question. What really happens when the wave function collapses? We know how to calculate the probabilities. We know which outcomes are likely and how the system behaves before and after a measurement. But the moment of collapse, the transition from the soft haze of possibilities to the single sharp fact of what is remains one of the most quietly profound mysteries in science. But then the real question rises quietly beneath all the math. What is it exactly that collapses, and why does it happen at all? Is collapse a genuine physical event, or simply the edge of our own understanding, an artifact of the way we ask questions about the universe? Physicists have proposed dozens of explanations, but none has settled the matter. Some believe we're missing a deeper layer of physics, that the process we call measurement is just a shadow of some more fundamental rule we haven't uncovered yet. Others are perfectly comfortable leaving collapse unexplained. If the predictions match reality with astonishing precision, they say then the mystery is philosophical, not scientific. But in quantum mechanics, philosophy isn't decoration, it's part of the puzzle. The nature of collapse speaks to the nature of the universe itself. Is reality fundamentally probabilistic? Does observation play an active role? Does the universe continually branch into parallel outcomes? Is information the scaffolding of existence, or is something even stranger waiting beneath the surface? We can picture collapse as the quantum world hardening into the classical one, a kind of phase transition like vapor cooling into a droplet. But unlike water, we have no clear pressure, no clear temperature, no clear threshold. All we know is that at some moment, the cloud of possibilities crystallizes and the universe chooses one version of itself. The metaphors are tempting, a veil dropping, a dream resolving, a menu of futures narrowing to a single choice. But maybe the wave function itself isn't what collapses. Maybe what collapses is our deeply human insistence that reality must always be definite, always be singular, always be one clean answer instead of a shimmering spread of options. Perhaps the universe is perfectly at ease with indecision. Perhaps we are the ones uncomfortable with it. And when we ask, what happens when we measure, maybe the deeper question is, what do we believe should happen, and are we prepared for the answer to be stranger and quieter than we ever imagined? If quantum physics had a birthplace, it would almost certainly be Copenhagen. Not because of the canals or the bicycles, but because it's where some of the most radical ideas in modern science were shaped, debated, and cautiously embraced. At the center of that intellectual storm stood Niels Bohr, a gentle, thoughtful physicist who had a talent for turning the universe inside out with a single sentence. Bohr helped shape what became known as the Copenhagen interpretation, one of the earliest and most influential viewpoints of quantum mechanics. The idea sounds simple, almost disarmingly, so according to this view, quantum systems don't have definite properties until they're measured. An electron doesn't occupy a fixed point in space. A photon doesn't settle on a single orientation. Nothing in the quantum world picks a clear state until an observation forces it to. Before that moment, reality is a blurred wave of possibilities. Measurement doesn't discover the outcome, it creates it. In this picture, the universe is a canvas waiting for the brushstroke of observation. A bold claim, the kind that makes philosophers lean forward and physicists quietly exhale. But Bohr and his colleagues weren't trying to mystify anything. They were following the experiments. Whenever they tried to treat particles as tiny solid objects, the math fell apart. But when they treated particles as waves of probability that only solidify under measurement, everything aligned. In the Copenhagen view, the wave function is not a physical ripple in space. It's a repository of everything that can be known, a structured list of possibilities. It describes potential, not presence, which leads to one of the interpretation's most provocative ideas. Questions about the system before measurement have no meaning. Asking where the electron really was before you looked is like asking the color of silence. The concept simply doesn't apply. Reality doesn't pre-exist for us to uncover. It locks into place only when we interact with it. The particle isn't hiding a truth. It simply doesn't have one yet. Understandably, not everyone found this view comforting. Albert Einstein, in particular, was famously troubled by the idea. He wanted a universe that existed fully and independently, regardless of whether anyone was watching. In his mind, reality shouldn't depend on attention. It shouldn't flicker into definiteness only when observed. It should simply be. To Einstein, the Copenhagen interpretation sounded uncomfortably close to saying the moon doesn't exist unless someone is looking at it. He found that deeply unsatisfying. Niels Bohr disagreed, of course, but not by offering some grand metaphysical argument. Bohr preferred a quieter kind of pragmatism. His view was that quantum theory tells us what we can say about nature, not necessarily what nature is. The role of physics in this frame is not to reveal the hidden gears of reality, but to describe experimental outcomes with perfect accuracy. If that feels like a partial answer, that's because it is. The Copenhagen interpretation is often criticized for exactly that reason. It feels less like a description of the universe and more like a set of instructions, a rule book for how to use the equations without worrying too much about what they mean. This attitude eventually crystallized into the now famous phrase, "shut up and calculate." Bohr didn't say it, but the spirit of it captured the mood of countless physicists who cared more about predictions than philosophy. And to be fair, the Copenhagen approach works. It underlies the physics behind semiconductors, lasers, MRI machines, and quantum computers. It predicts experimental outcomes with astonishing reliability. It has never been contradicted by data. For many scientists, that's enough. But the philosophical discomfort never fully disappears. If the universe only takes on definite properties, when measured, what does that imply about the cosmos long before conscious observers existed? Was the early universe sitting in some quantum limbo, waiting for anyone to look? Most physicists would say no. The Copenhagen interpretation doesn't require consciousness, only interaction. In this framework, a measurement is any process that extracts information from a system and forces it into a definite state. A detector, a molecule, a passing photon, any of these can observe in the quantum sense. But even that raises new questions. What exactly counts as a measurement? At what threshold does the wave function collapse? Why does nature follow this rule at all here? The Copenhagen answer tends to trail off into gentle ambiguity. The theory doesn't say why collapse happens. It simply tells you when it shows up in practice. And if that's not satisfying, you're invited to explore one of many alternative interpretations. Interpretations like many worlds. Pilot wave theory and objective collapse models all attempt to restore some classical intuition, ideas like definite reality, local cause and effect, or observer independent existence. But each of those alternatives comes with its own strange consequences. None of them let you walk away untouched. Each one forces you to give up something. Locality determinism, uniqueness of outcomes, or even the very idea that the universe has a single storyline. And in that tension, quantum mechanics continues to sit powerful, precise, undeniably correct, and yet wrapped in a silence about what reality truly is beneath the equations. Copenhagen, by contrast, feels almost minimalist. It doesn't rely on hidden variables or hidden layers of reality. It doesn't summon countless branching universes. Instead, it offers a compact set of instructions: calculate the wave function, apply the measurement rule, and read off the probabilities. Clean, direct, functional, and perhaps that's where its quiet strength lies. In a domain filled with deeply strange possibilities, the Copenhagen interpretation gives you something steady to hold on to. It doesn't pretend to solve the deepest riddles. It simply gives you a framework that matches the world we can probe, test, and interact with. Bohr often described this approach with language that felt almost philosophical. He once said that anyone who encounters quantum mechanics for the first time without feeling shock must not have truly grasped it. He understood that Copenhagen wasn't about explaining the universe's hidden machinery. It was about learning to live with uncertainty, not as a failure of knowledge, but as a built in feature of nature. Quantum mechanics is undeniably strange, but rather than force that strangeness into a familiar shape, the Copenhagen view invites us to accept the unfamiliar and work within it, not as a final answer, but as a practical guide, a reminder that in the quantum world, clarity and discomfort often sit side by side, and that sometimes the most honest response is simply to shut up and calculate. Now imagine holding a coin between your fingers. You flick it upward, it spins, flashes, and lands on your palm. Heads. But according to one of the boldest interpretations of quantum physics, that single outcome is only one thread of a far larger tapestry. In another branch of reality, the same coin has landed tails. In yet another, it wobbled, tipped, and rolled off the table. Every possible result of that flip unfolded fully physically, not as a hypothetical, but as a real version of events. You experience only one, the others happen elsewhere. This is the heart of the many worlds interpretation. It emerged as an attempt to rethink the wave function collapse problem, that puzzling moment when quantum possibilities seem to snap into a single outcome. In the traditional Copenhagen view, a measurement forces that collapse. One option becomes real, the rest disappear. But what if the collapse never occurs? What if the wave function continues its evolution smoothly without ever deleting any possibilities at all? That was the radical proposal put forward by physicist Hugh Everett III in 1957. In his view, the wave function never breaks, never chooses, never cancels outcomes. It simply unfolds according to the equations, like a branching river. Every measurement doesn't eliminate possibilities, it separates them. The universe doesn't pick one outcome, it contains them all. Maybe Everett suggested when you measure a system, you're not forcing it to make a choice. You're not collapsing anything. Instead, you're separating. The act of measurement doesn't select one reality, it divides reality into versions that hold every outcome. Each possibility unfolds, but in its own isolated branch. It sounds dramatic, almost like the plot of a cosmic novel, but Everett wasn't writing fiction. He was following the mathematics to its most literal conclusion. In his framework, quantum mechanics works exactly as it always has, minus the single extra rule that says the wave function must collapse when we look. Remove that rule, and everything becomes continuous, smooth branching. The wave function never snaps, it simply evolves. Consider an electron with two possible spin states up and down. In the traditional view, the electron sits in a superposition of both until you measure it, and the measurement forces a choice. Everett's view is different. When the measurement occurs, the system plus the observer split into two correlated versions of reality. In one branch, you see spin up. In another, you see spin down. Both branches are valid. Both outcomes exist. And both versions of you go on with their own histories. No collapse, no randomness, just a continuous branching flow of quantum evolution. To many people, this sounds like an overwhelming idea, parallel universes multiplying endlessly, shadow versions of you making every possible alternative choice. But the many worlds interpretation doesn't require new forces or speculative mechanisms. It simply takes the existing equations at face value and refuses to add unnecessary extras. To its supporters, this is its beauty. The worldview may be vast, but the mathematics is clear and uncluttered. Still, not everyone finds comfort in this infinite branching. If the universe is constantly splitting, where do all these branches reside? Are they layered atop one another, like overlapping sheets of reality? Are they drifting in some higher dimensional structure many worlds doesn't specify? It isn't a geometric theory about space itself. It's a statement about how quantum states evolve. The branches are real, but they don't interact. Once the split occurs, decoherence kicks in. The branches lose all ability to interfere or exchange information. They become mutually invisible, like rooms whose walls can never be crossed. And that raises a hard question. If the other branches can't be observed even in principle, how could we ever test whether they exist? Critics point to this as the heart of the problem is an interpretation that multiplies universes but hides them forever, truly scientific. Supporters counter that this objection misses the point. They argue that many worlds isn't adding anything extravagant, it's removing the least elegant assumption in quantum theory, the collapse postulate. If the Schrödinger equation never asks for collapse, why invent it? In their view, collapse is the complication. Branching is the simplicity. Occam's razor cuts in two directions here. Copenhagen keeps the universe small, but adds a rule that doesn't appear in the math. Many worlds removes the extra rule, but accepts a universe unimaginably vast. And how vast? Consider this quietly, like watching ripples spread across a calm lake. Every quantum event with multiple outcomes, every photon scattering, every molecular vibration, every atomic transition causes branching. Not occasionally, not rarely, constantly. The universe isn't splitting in dramatic cosmic moments. It's branching all the time, everywhere, at every scale. A quiet, ceaseless unfolding of possibilities into parallel histories. The picture is enormous, uncomfortable, maybe even overwhelming. And yet, beneath that immensity lies an oddly peaceful idea. The equations never break. They never hesitate. They never choose. They simply allow everything that can happen to happen, just not all in the same place. We don't feel the branching for the same reason we don't feel the earth spinning beneath us. It's happening constantly, quietly, but it leaves no trace in our senses. From our point of view, everything looks singular and tidy. We witness one outcome and assume that's the whole story, unaware that countless other versions unfolded just beyond our reach. It's also important to remember that in the many worlds picture, these parallel outcomes aren't science fiction scenarios where you jump between timelines or compare notes with another version of yourself. The branches don't mingle, they don't swap information. Once they separate, they drift apart permanently, like ships sailing into different fogs. Each contains a consistent reality, but none can observe or influence the others. This simplicity removes many of the conceptual tangles found in collapse based interpretations. You never have to decide what counts as a measurement or where the boundary between observer and system sits. There's no moment where the universe stutters and chooses. Everything flows continuously, and measurement is simply the process of becoming entangled with what you observe. You and the system join in a single quantum description, and the world unfolds from there. But this clean elegance raises a profound question. If all outcomes occur, why does it feel like only one did? Why does the coin seem to land heads and not tails? Why do you experience a single thread instead of a tapestry in many worlds? Probability means something slightly unfamiliar. It's not the chance that one outcome happens instead of another. It's the measure of how much of you ends up in each branch. Some branches are thicker, more heavily weighted, meaning more of your future observers experience a particular result. Others are thinner, representing less of your future experiences. It's not intuitive, but then again, almost nothing in quantum mechanics is. Despite its oddness, many worlds has inspired serious scientific work. Some researchers think it might help bridge the gap between quantum mechanics and gravity. Others point to its natural compatibility with quantum computing, where superposition and entanglement process information across multiple pathways at once. And philosophically, it offers its own kind of comfort or discomfort depending on your temperament. In this framework, no possibility is ever thrown away. Every branch persists, every choice lives on. The roads you didn't take aren't erased, they simply belong to other versions of the unfolding universe. This doesn't mean you should imagine a chaotic cluster of universes stacked like comic book panels. Instead, picture a vast, quiet tree growing endlessly, each new branch, a subtle divergence, each leaf, a complete and self contained world. All possibilities accounted for, all real in their own quiet way. And now shift your attention from branching universes to something even deeper, the material of reality itself. Imagine pulling back the veil on everything around you, the stars overhead, the floor beneath you, your breath, the warmth rising on your skin. What if all of it, every atom, every beam of light, wasn't made of hard pieces at all? What if the most basic ingredients of existence weren't particles but vibrations? Waves moving through invisible fields that fill all of space. Welcome to the world of quantum field theory, or QFT, where the universe isn't built from tiny solid objects, but from ripples in fields that stretch everywhere. Let's start gently. In classical physics, a field is something that gives every point in space a value. Think of an electric field. It doesn't look like much, but place a charged particle within it, and the particle feels a push. The field extends through space, shaping how things move, like an invisible ocean with currents you can only infer from their effects. Quantum mechanics adds a twist. It says fields aren't calm or continuous. They fluctuate constantly. Even when you remove all particles and strip away all energy, you can measure the fields never fully settle. They quiver with uncertainty, stirred by the same quantum rules that govern electrons and photons. And here's the profound leap in quantum field theory: everything is a field. Every particle you can name, electrons, photons, quarks, neutrinos, is simply a small localized disturbance in a deeper field that permeates the universe. A particle isn't a tiny sphere racing through space. It's a ripple, a knot of energy, a brief shimmering in a vast underlying ocean. Take the electron, for example. Somewhere, everywhere, woven through all of space, there exists the electron field, a quantum field that never switches off, never disappears, never takes a break. When you notice an electron in an atom or watch it flicker across a detector, you're not observing a tiny independent object. You're seeing a small localized disturbance in that universal field, a momentary pulse, a tiny quantized quiver. The particle is simply the field expressing itself in one particular spot. The same is true for photons. The electromagnetic field permeates all of space, stretching out like a silent ocean. A photon isn't a miniature pellet racing through the void. It's a brief vibration, a tap on the surface of that field. Change the rhythm of that vibration, and you get red light. Adjust it differently, and you get ultraviolet radiation, or radio waves, or X rays. They're all just variations of the same field humming at different frequencies. And this idea extends everywhere. We have quark fields, gluon fields, neutrino fields, the Higgs field. Even gravity, if we ever manage to quantize it, would show up as tiny ripples in an underlying gravitational field. In this picture, the particle isn't the foundation, it's the footprint. The field is what exists. The ripple is what we observe. This shift in perspective is enormous. Instead of imagining reality as a collection of tiny solid pieces stacked together like microscopic building blocks, quantum field theory paints the universe as something fluid, more like a vast symphony of overlapping vibrations, each note blending with the next. What we call matter is really just particular patterns emerging from these deeper waves. And suddenly, a lot of confusing quantum behavior begins to make sense. Consider what happens when particles are created or destroyed in high energy collisions. In classical thinking, matter can't simply appear or vanish. But in the quantum field view, nothing magical is happening. Feed enough concentrated energy into a region of space, and you can excite a field strongly enough to produce a new ripple, what we identify as a particle. That's why particle accelerators can generate completely new forms of matter from what looks like empty space. Even antimatter fits neatly into this framework. The positron, the electron's opposite twin, is simply another allowed mode of vibration in the electron field, one with inverted charge and reversed properties. It's not mysterious. It's symmetry written into the fabric of the field itself. The forces between particles also fall naturally out of this framework. Electromagnetic attraction or repulsion isn't some invisible hand pulling or pushing objects. It's particles exchanging photons, little ripples in the electromagnetic field. The strong force that binds quarks together arises from gluons vibrating in their own field. And if gravity eventually joins the quantum family, it will likely do so through hypothetical gravitons. Yet another ripple, another pattern in a deeper field. Even the vacuum that's supposed at emptiness refuses to be empty. Quantum field theory says the fields that fill space can never rest completely. They fluctuate even in perfect darkness. Tiny bursts of energy appear and vanish, shaping subtle forces like the Casimir effect, where two metal plates placed closely together feel a gentle attraction because the vacuum between them holds fewer allowed fluctuations than the space outside. There's something profoundly peaceful about this picture. Space isn't a silent stage waiting for particles to move across it. Space is alive. Every location in the universe participates in this subtle, ever present motion. Every interaction you ever learned about light bouncing from a surface, atoms bonding matter forming, begins as a coordinated dance of these fields. Of course, the mathematics behind QFT is famously complex. You don't solve it with a quick sketch on a cafe napkin unless that napkin stretches across a lecture hall and you happen to have Feynman diagrams handy. But the conceptual message is beautifully simple. At the deepest level, nature is not made of objects. It's made of excitations, patterns, structured vibrations in space and time, even mass. The weight we associate with solid matter often arises from interactions with underlying fields, not from any inherent stuffness in the particles themselves. The Higgs field, the quiet background field, confirmed experimentally in 2012, plays a remarkable role in this story. It's the mechanism that gives many fundamental particles their mass. In the language of quantum fields, mass isn't an intrinsic weight tucked inside a particle. It's a measure of how strongly that particle interacts with the Higgs field as it moves through space. Some particles glide through effortlessly. Others feel resistance almost as if they're trying to swim through something thick and sticky. The stronger that resistance, the heavier the particle appears, which means that here in this moment, your body, your thoughts, your heartbeat are not made of tiny isolated objects. You are a coordinated pattern within a tapestry of fields. Your electrons are gentle ripples in the electron field. Your quarks are small disturbances in the quark field. Every photon that ever touched you was a momentary vibration in the electromagnetic field. Even the atoms in your bones are stable only because these fields weave together in just the right way. The boundary of you isn't the surface of your skin. The fields that define you extend outward, interacting with the fields that define everything else. There's no hard shell locking you and no sharp edge where your existence stops. Instead, there's a gradual fading of amplitude, a soft blending between your fields and the rest of the universe. We are not separate structures sitting inside space. We're patterns within space, shaped by the quiet, constant motion of fields. Quantum field theory doesn't merely describe the universe, it is the framework through which the universe expresses itself. The most complete map we've drawn so far shows reality not as a collection of particles bumping around like microscopic marbles, but as an intricate orchestra of fields playing in coordinated, ever shifting patterns. A symphony too fast, too subtle, too intricate for our senses to resolve directly. And if you're still awake, if your thoughts haven't drifted too far into the edges of sleep, you might be wondering if every particle is a vibration, every force a ripple. What is the thing beneath it all? What medium do these fields ripple through? That, dear listener, is a question waiting patiently for another night. For now, let's turn gently toward another piece of the cosmic puzzle, the standard model of particle physics. If the universe had a recipe book, this would be its ingredient list, minus a few missing spices, mysterious ones like dark matter and dark energy that we still haven't identified. For all its quirks, this model is astonishingly successful. It outlines the fundamental components of reality, the forces that connect them, and the rules that determine how everything interacts. At its core, the standard model organizes the universe's most basic building blocks into a few elegant categories: quarks, leptons, and bosons. These particles aren't made of anything smaller, at least as far as our deepest experiments can tell. Think of them as the alphabet from which everything else is written. Quarks come first. They're the ingredients inside protons and neutrons, the solid nuclei inside atoms. There are six kinds called flavors up, down, charm, strange, top, and bottom. The names may sound whimsical, but the physics they represent is anything but. The up and down quarks form nearly all familiar matter. A proton is two ups and one down. A neutron is two downs and one up. Everything you see, everything you've touched today, everything you are, is built mostly from these two flavors, plus the plus electrons. The remaining quarks, charm, strange, top, and bottom, are heavier, more exotic, and far less common. They appear only fleetingly in the high energy collisions of cosmic rays or in particle accelerators shining for the briefest instant before decaying. They're the guest stars of the particle world, dramatic, rare, and essential to the full cast, even though they don't linger. Next come the leptons. The familiar electron is here, zipping around atoms, carrying charge, enabling chemistry and electricity. But electrons have heavy cousins, the muon and the tau. They behave like electrons, but with far more mass, appearing briefly in high energy conditions before vanishing again. Each charged lepton comes paired with a neutrino 3 in total. These neutrinos are astonishingly light and almost ghost-like. They pass through planets, stars, and your body with barely a whisper of interaction. Billions stream through you every second, unnoticed and untouched. They're the quiet wanderers of the universe, present everywhere, yet rarely acknowledged. So far, we've met the quarks and the leptons, six of each neatly arranged into three generations. 12 matter particles forming the raw material of everything familiar. But matter by itself doesn't create a universe. Something has to tell it how to behave, how to attract, repel, bind, scatter, or decay. That's where the bosons enter the stage. Bosons are the messengers. They're the carriers of the fundamental forces, the quanta, that allow particles to influence one another. You can think of them as tiny packets of interaction, little notes passed across the quantum classroom that say, move this way or change that property. For the electromagnetic force, the messenger is the photon, the quantum of light. The photon is massless and moves at the cosmic speed limit. Whenever an electron feels a tug from another charged particle, it's because a photon has been exchanged between them. Without this constant photon chatter, atoms couldn't hold together, molecules couldn't form, and life, along with your morning coffee, would simply never happen. The weak nuclear force responsible for events like radioactive decay has three carriers, the W plus, the W, and the Z boson. These bosons are enormously heavy, which limits the reach of the weak force to tiny scales inside atomic nuclei. Despite the name, the weak force plays a crucial role in shaping the universe. It changes neutrons into protons and protons into neutrons. It helps power stars. It's weak only by comparison, but essential in every sense. Then there is the strong nuclear force, the mighty glue that binds quarks together inside protons and neutrons. Its bosons are called gluons, massless, energetic, and produced in 8 varieties. Gluons hold quarks, in an endless exchange of energy, a chaotic, restless dance that keeps atomic nuclei intact. Without the strong force, matter would simply fall apart into a sea of unbound particles. And finally, the most recent addition, the Higgs boson. Confirmed in 2012 at CERN, it's the quantum ripple in the Higgs field, the field that permeates all of space and grants mass to many elementary particles. Without the Higgs mechanism, the Standard Model's universe would be unrecognizable. Most particles would move at light speed, unable to slow down enough to clump into atoms. Everything would behave like pure radiation. Instead, the Higgs field provides resistance, a gentle drag that gives different particles their mass and makes stable matter possible. So, stepping back for a moment, we have 12 matter particles, 6 quarks, and 6 leptons. We have the bosons, photon, WZ, gluon, and Higgs. Together, they form the Standard Model, the concise yet powerful framework that describes nearly every known particle interaction. And the remarkable part, it works with precision that borders on uncanny. Particle accelerators test it relentlessly. Every radioactive decay, every scattering pattern, every collision outcome, it predicts them with extraordinary accuracy. The model isn't perfect, but within its domain, it performs like clockwork. Yet the Standard Model has blind spots. It says nothing about gravity, which still lives in the realm of Einstein's general relativity. The two frameworks, quantum mechanics and gravity, speak different mathematical languages. Reconciling them remains one of the deepest unsolved challenges in physics. It also cannot explain dark matter, the invisible mass shaping galaxies and cosmic structures. None of the Standard Model's particles have the right properties to account for this hidden substance, nor does it include dark energy, the mysterious driver behind the accelerating expansion of the universe. In fact, when you add everything up, the atoms, the light, the forces, we understand the Standard Model accounts for only about 5% of the cosmos. A precise, well tested 5%, but still just a small slice of the grand picture. And that's why physicists sometimes describe the Standard Model as complete yet deeply unsatisfying. It captures the part of the universe we can touch, test, and measure, but it leaves vast cosmic territories unexplored, a familiar island floating in an ocean of unknowns. It's a bit like finishing a puzzle, only to realize that the picture you completed is just a tiny corner of a far larger mural. Still, what we can see is extraordinary layers of symmetry, subtle repetitions, and mathematical relationships that suggest an underlying unity waiting quietly beneath the surface. Some physicists believe that all these ingredients, quarks, leptons, and bosons, might eventually merge under a deeper framework, a grand unified theory, or perhaps even a complete theory of everything. These possibilities are still out of reach experimentally, but the hope comes from the same curiosity that built the Standard Model in the first place, a belief that nature hides patterns, and that with enough patience, those patterns reveal themselves. So when someone casually asks what the universe is made of, you can almost smile and say, mostly quarks, a few leptons, and a handful of bosons holding everything together. Then, if you're feeling playful, you can add, and don't forget the Higgs field. Without it, nothing would feel heavy at all. It's not the full story, not even close, but it's a surprisingly solid introduction. Now, if the standard model is the ingredient list, quantum electrodynamics QED is the part of the cookbook that describes how light and matter talk to each other. And in the realm of precision, QED sits at the very top. It's often described as the most accurate physical theory ever constructed. Every flick of electricity, every glimmer of light, every subtle push between charged objects is governed by its rules. For all its complexity, it matches experimental results to an astonishing degree, sometimes to better than one part in a billion. Imagine stretching a measuring tape across an entire continent and getting the answer right down to the width of a single human hair. QED performs at that level. To understand why this is such an achievement, it helps to look at where the problem began. Early physicists knew that electrons interacted with electromagnetic fields. They knew electrons could emit or absorb light and jump between energy levels. But when they tried to calculate the details mathematically, everything broke. The equations misbehaved, blowing up into nonsensical infinite values. The moment they tried to analyze even a simple process like an electron emitting a single photon, the math would produce infinite energy. Obviously, the universe does not function that way, and yet the equations insisted otherwise. Then came the breakthrough. Richard Feynman, along with Julian Schwinger and Sin Itiro Tominaga, found ways to reorganize the theory so the infinities could be tamed and replaced with meaningful results. But Feynman added something no one had expected of visual language. He introduced Feynman diagrams, tiny sketches that turned complicated quantum interactions into simple pictures. These diagrams showed particles as lines and their interactions as junctions or loops, with time flowing gently from one side to the other. An electron might travel across the diagram, emit a photon, and then continue onward. That photon might fly off and strike another electron, or loop around and briefly interfere with the same one. Each of these possible paths has a mathematical weight, and QED requires you to add every single possibility together. Not just the simple ones, not just the intuitive ones, all of them. Even bizarre scenarios count. An electron emits a photon, which momentarily becomes an electron-positron pair, which then annihilates into another photon, which is then reabsorbed. These strange participants are called virtual particles. They never appear directly in our detectors, but they influence the outcome in ways the equations can capture. This is where QED begins to feel less like a set of rules and more like a soft, strange quantum tapestry. The theory doesn't just predict what does happen, it predicts what could happen and folds those possibilities into the final answer. Every loop, every twist, every hypothetical fluctuation shapes the ultimate behavior of the electron. One of QED's proudest successes is explaining the tiny deviation in the electron's magnetic moment, the so-called anomalous magnetic moment. Classical physics predicts a value, but experiments show a slight difference. QED calculates that difference with almost impossible accuracy, matching experiments to over 10 decimal places. That level of precision still amazes physicists. QED also naturally handles phenomena like Compton scattering, where photons bounce off electrons, radiation emitted when charged particles slow down, and even pair production, where light transforms into an electron and a positron. These processes, strange and sometimes violent on the quantum stage, unfold cleanly inside QED's mathematical framework. For a theory born out of chaos and infinities, QED has become a model of elegance. It turned a confused field of equations into a coherent description of how light and matter weave together. And through its diagrams, loops, and probabilities, it reveals something quietly profound beneath all the complexity. Nature behaves with remarkable consistency. What QED gives us is not just accuracy, it gives us a glimpse of order inside the quantum haze, showing how even the smallest interactions follow patterns as delicate and intricate as lace. All of these processes, even the ones that sound like incantations from a far future science fiction novel, fall naturally out of the QED framework. And QED doesn't exist in isolation. It's the quantum field the theory that governs electromagnetism, but it also became the blueprint for the theories that followed. The strong force has its own shimmering counterpart, quantum chromodynamics. The weak force blends seamlessly with electromagnetism in the electroweak theory. But QED came first, and in many ways it set the tone for how modern quantum field theories would work. What makes it charming is that despite the labyrinth of its mathematical machinery, the core idea behind QED is almost disarmingly simple once you feel its rhythm. Richard Feynman liked to say the rules could fit on the back of a napkin. Particles take every possible path. Every path has a complex amplitude. You add them all, square the total. That's the probability. Everything else is just the universe keeping track of its own possibilities. This idea that nature explores every route simultaneously is at the heart of the quantum worldview. An electron doesn't travel from point A to point B like a marble rolling down a track. It drifts through every corridor, at once slips past every obstacle, weaves through every whisper of open space. The universe is always tallying all those possibilities, and QED is the language that lets us glimpse the calculation. For all its elegance, QED also has boundaries. It doesn't include gravity, and it offers no insight into dark matter or the unseen mass shaping galaxies. But within its domain, it's unmatched, still the most accurately tested theory in the history of science. Even Feynman, who disliked reverence of any kind, admitted that QED was extraordinary. Yet he also warned that nature is endlessly inventive and that any theory we build is probably just an approximation of something deeper. Still, QED stands as a masterpiece, for now a theory born from mathematical chaos and conceptual frustration that somehow resolved into a clear, almost serene description of how light and matter exchange whispers. It governs the shine of distant stars, the glow of your phone screen, the quiet lamp beside your bed, all choreographed by a quantum dance so subtle you rarely notice it happening, even though it occurs billions of times each second with flawless consistency. Quantum electrodynamics is a quiet triumph, an invisible symphony of photons and fields playing continuously beneath everything. And from this strange quantum bedrock emerges something even more astonishing: quantum computing. If classical computers behave like disciplined librarians, methodical, organized, flipping through information one page at a time, then quantum computers behave like eccentric poets, reading every page of every book simultaneously in overlapping probabilities. It feels like magic, and in some sense, it is the closest thing physics gives us to it. But quantum computing is built on solid quantum principles, the same ones that let electrons tunnel through barriers and particles entangle across continents. To see why quantum computers are different, you first need to meet the bit's peculiar quantum sibling, the qubit. Classical computers reduce everything to bits zeros and ones, off and on, tidy and definite. Your browser, your videos, your bank account, all encoded in those binary yes or no states. But a qubit doesn't live in such a confined space. Thanks to superposition, a qubit can inhabit a blend of 0 and 1 at the same time, like a coin spinning in midair, not choosing heads or tails until you catch it. While that quantum coin spins, it holds the potential for both outcomes in a single breath. And as you add more qubits, the power of that layered potential grows exponentially. 2 qubits hold 4 possibilities, 3 hold 8, and 20 hold over 1,000,000. With enough qubits, a quantum computer can explore an astronomical landscape of possibilities in parallel, effortlessly wandering go through an ocean of outcomes that a classical computer could never hope to examine in any reasonable time. That's the central idea beneath quantum computing: parallelism unfolding in a way classical machines can't imitate. While a traditional computer tests possibilities step by orderly step, a quantum computer spreads its awareness across many routes at once. Not in a way that instantly hands you every answer, but in a way that lets you shape the probability landscape, so that when you finally observe the system, the most meaningful answer rises naturally to the surface. It isn't brute force searching, it's sculpting likelihood itself until the correct solution becomes the most stable, the most resonant, the most probable expression of the system. And quantum computing has another remarkable gift in its toolkit: entanglement. When qubits become entangled, their states interlock so deeply that what happens to one echoes in the other, even if they're separated by great distances. It's a kind of synchronized movement, a silent choreography between quantum dancers. One shifts, the other responds instantly, held in an unbreakable correlation that no classical bit could ever reproduce. Through these entangled links, quantum computers can perform operations that classical machines would need immense time and energy to simulate. For certain tasks like modeling molecules, predicting chemical behavior, or factoring enormous numbers, quantum approaches promise leaps in speed and complexity that simply aren't possible otherwise. But here is where we settle, breathe, and remember the bigger picture. Quantum computers are not poised to replace the device on your desk. They are specialized instruments crafted for specific kinds of problems, not everyday tasks like browsing, editing, or streaming. Your classical processor remains unparalleled for the familiar routines of daily life. And building a quantum computer is immensely challenging. Qubits are fragile, so delicate that a passing vibration, a small temperature shift, or even a wandering magnetic field can disrupt them. Their coherence, the very quality that allows them to exist in superposition and entanglement, fades with even the slightest interference. Many quantum systems must be cooled to temperatures near absolute zero, colder than the void between stars, just to remain stable. Then comes the obstacle of error correction. In classical computing, correcting a flipped bit is straightforward. In quantum systems, it's far trickier. You can't make perfect copies of a quantum state. The no cloning theorem forbids it. So scientists have devised sophisticated techniques that bundle many physical qubits together to safeguard one logical qubit. It's like wrapping a delicate whisper in layers of shielding so it can be preserved long enough to be heard clearly. Even with these hurdles, progress has been remarkable. Research groups and companies around the world have built machines with tens, even hundreds of qubits. Some have demonstrated quantum supremacy by performing calculations that would be impractical for classical supercomputers. Others are working with what we call NISQ devices, noisy intermediate scale quantum machines that explore what can be achieved even with imperfect qubits. And slowly, real world applications are emerging. One of the brightest frontiers is quantum chemistry. Simulating molecules at the quantum level is extraordinarily difficult for classical computers, but quantum processors mirror those behaviors naturally. This could reshape material science, drug design, clean energy research, and the search for next generation batteries. Another promising direction is optimization problems with many competing variables, like mapping efficient supply chains or distributing global resources. Quantum algorithms might discover optimal solutions faster or in ways classical machines can't. And then there is the realm of cryptography. Algorithms like Shor's could one day break widely used encryption systems by factoring massive numbers with astonishing speed. This has sparked the rise of post quantum cryptography security designed to withstand the power of future quantum machines. But it's important to acknowledge where we stand. Today's quantum computers are noisy, easily disturbed, and limited in capability. The dream of a large scale, fault tolerant quantum machine remains years, possibly decades away. Yet that doesn't diminish the wonder. Each step forward is a quiet revelation, a glimpse into how information behaves in the quantum world. And the journey itself is reshaping how we understand computation reality and the subtle architecture of the universe. What's particularly enchanting is how quantum computing doesn't run from the strangeness of quantum mechanics. It embraces it gently, almost artistically. The very features that once felt like riddles, designed to haunt physicists, superposition, entanglement, the collapse of possibilities become tools, ingredients, creative techniques. Superposition stops being a conceptual headache and becomes a reservoir of parallel potential. Entanglement, once dismissed as spooky nonsense, becomes a channel through which information flows with uncanny coherence. Even measurement, the act that snaps uncertainties into a single outcome becomes an intentional step in a computation. The wildness isn't suppressed, it's directed, not tamed by force, but guided like wind filling a sail. Quantum computers ask us to update our intuition. They invite us to consider that information can be soft overlapping, shimmering with multiple futures. That logic can be probabilistic without being chaotic. That answers may arise from entire landscapes of possibilities rather than one carefully traced path. And although we don't yet know where this evolving technology will ultimately lead, the journey itself is quietly transformative. It's reshaping the boundary between machine and mind, between certainty and uncertainty, between what we can build and what we can imagine. And this strangeness isn't limited to the cold vacuum of physics labs. It's beginning to appear somewhere even more surprising inside the living world. Biology, unlike the pristine environment needed for delicate quantum states, is warm, noisy, molecularly chaotic. It's a landscape full of collisions, vibrations, and chemical storms. Quantum effects should theoretically fall apart instantly, and yet life seems to be playing with quantum rules in ways we're only beginning to understand. Consider the humble robin, a small, unassuming bird with an astonishing ability to navigate thousands of miles with near perfect accuracy. For decades, scientists suspected birds carried some kind of internal compass, but the mechanism refused to reveal itself. Then came a hypothesis so bold it sounded like fiction. The robin might be seeing Earth's magnetic field using quantum entanglement. Deep in the bird's eye, there appears to be a molecule, likely cryptochrome, capable of hosting a pair of electrons that become entangled when struck by light. Their linked spins respond subtly to Earth's magnetic field, altering chemical reactions in a direction dependent way. The bird isn't consciously aware of any of this, yet it experiences a faint visual cue, a pattern or shading aligned with north, a quantum compass built into biology. Skeptics understandably pushed back. Entanglement is fragile, so fragile that even a stray photon can unravel it. Could it possibly survive inside a warm cell teeming with activity? And yet, experiment after experiment has hinted that nature may indeed be maintaining entanglement inside living systems. Something our most refined machines still struggle to do consistently. If this proves true, it means life discovered quantum engineering long before we did. Plants offer a second example of nature's quiet quantum brilliance. Photosynthesis, the process that powers almost all life on Earth, seems simple at first glance. Sunlight hits a chlorophyll molecule, energy is absorbed. That energy travels to a reaction center where it's locked into chemical form. Straightforward, efficient. But efficiency is the mystery. How does the energy move through the molecular maze so quickly and with so little loss? You might imagine it hopping randomly from molecule to molecule, like a person stumbling through a dark room. But randomness is slow, clumsy, inefficient, and plants are anything but clumsy. What researchers discovered is extraordinary. The energy doesn't hop, it spreads. It explores multiple paths simultaneously, as if the plant were testing all possible routes at once. A quantum superposition guiding energy through its internal architecture with near perfect efficiency. The energy takes every path, interferes with itself, and naturally selects the fastest route long before a classical system would stumble its way there. Life messy and warm and vibrationally chaotic is somehow harnessing quantum coherence, something we fight desperately to maintain inside our most advanced machines. It's a reminder, whispered softly through biology itself, that the quantum world isn't separate from the living world. It underlies it, it shapes it, it breathes through it. And sometimes, when conditions are just right, life uses the deep rules of the universe not by accident, but with elegant purpose. But measurement hints that something much more subtle is happening inside the leaf. The energy doesn't wander one corridor at a time like a lost traveler. It seems to spread across many paths simultaneously, as though the system momentarily becomes a quantum wave, feeling every route, sampling every possibility before settling into the one that delivers energy with near perfect efficiency. Imagine dropping a marble into a maze, except instead of rolling left or right, it ripples outward like water, touching every wall, every corner, every passage at once, and then instantly choosing the fastest escape. That's the kind of behavior researchers believe these photosynthetic complexes may be performing. It isn't random, it's coordinated, and astonishingly, it happens in warm, noisy, biological environments where coherence should collapse almost instantly. Yet somehow, these quantum ripples persist just long enough, mere picoseconds, but an eternity at molecular scales, to steer energy with extraordinary precision. If plants really are quantum navigators, it raises a striking possibility. Evolution may have discovered quantum optimization long before humans built their first qubit. Biology had billions of years to experiment and refine and stumble upon molecular architectures that preserve coherence just long enough to matter. That means some organisms might naturally harness the quantum rules we consider exotic. And if plants can do it, perhaps other senses can too, like smell. Most people imagine the sense of smell as a mechanical process. A molecule fits into a receptor like a key sliding into a lock, and boom, ascent detected. But this shape only model runs into problems. Molecules with almost identical structures can smell nothing alike, while chemically different molecules can smell surprisingly the same. That inconsistency led to an alternative idea, the vibrational theory of olfaction. It proposes that receptors in your nose might detect not only a molecule's shape, but also the frequency at which it vibrates. When the molecule binds to a receptor, electrons inside that receptor might quantum tunnel through it, and the probability of tunneling depends on the molecule's vibrational signature. If true, it means part of your everyday experience, detecting a lemon, a rose, a cup of coffee, may rely on the same quantum tunneling that powers nuclear fusion in stars. Evidence is still emerging, but experiments with humans and even fruit flies show that organisms can sometimes distinguish molecules that differ only in vibrational frequency. It isn't definitive, but it's enough to keep the field alive. Quantum biology is young, full of bold ideas, delicate experiments, and unanswered questions. But its promise isn't just novelty, it's the reminder that quantum physics doesn't shut off when things get warm and biological. It spills into the feathers of a migrating bird, the shimmering architecture of a leaf, and the chemical dances and pimentas happening in your own nose. The mathematics that describes electrons flickering in a vacuum also shapes the robin's ability to navigate and the way a plant catches sunlight. Nature doesn't divide itself into categories the way humans do. Quantum rules are not confined to laboratories, they permeate life itself. And perhaps as we uncover these quantum strategies, we'll gain not just new technologies, but a deeper admiration for the way evolution quietly repurposes the universe's strangest tools. Because in truth, life has been fluent in quantum mechanics for billions of years. We're only now learning how to listen. At the quantum scale, particles behave like soft clouds of probability. They interfere, superpose, and drift through possibilities. But the world you touch, your desk, your coffee mug, your cat curled on the blanket, behaves nothing like that. You don't see chairs that are both here and across the room. You don't encounter sandwiches existing in overlapping probability waves until you open the fridge. Reality feels stable, definite, classical. So, why doesn't the quantum weirdness of the microscopic world show up in everything around you? The answer is a quiet, powerful process called decoherence, the mechanism by which the sharp, delicate strangeness of quantum behavior gradually dissolves into the familiar classical world you experience every day. Decoherence also plays a quiet but important role in how we interpret the quantum world itself. It doesn't give us the final answer to what reality is, but it shows us why the classical world feels so stable. It explains why your keys stay in your pocket, why a cup sits firmly on the table, and why you never witness the ghostly interference patterns that electrons display in a vacuum chamber. It gently reminds us that the classical world isn't separate from quantum mechanics. It's an emergent layer sitting on a top of it, shaped by constant interactions with the environment. Different interpretations of quantum mechanics build on this idea in their own ways. In models like many worlds, decoherence is the quiet mechanism that splits branches apart, preventing different outcomes from interfering with one another. In collapse theories, decoherence helps determine when quantum behavior gives way to definite outcomes. Even in the Copenhagen interpretation, decoherence acts as the bridge between the wave of possibilities and the world we actually observe. It doesn't answer the deepest philosophical questions, but it shows us how the quantum fog condenses into familiar form. And perhaps the most comforting part of all is this decoherence doesn't mean the quantum world disappears. It doesn't mean superpositions stop existing or that probabilities lose their richness. It simply means the delicate quantum threads become woven into the vast vibrating tapestry of the environment. They spread out, get absorbed, get blurred until the details dissolve into the background and the system appears classical. You can think of it like trying to listen to a single, quiet violin in a roaring symphony hall. The violin is still playing, but the orchestra around it is so loud, so overwhelming, that the delicate melody becomes impossible to isolate. Decoherence is that orchestra nature's constant background noise washing over quantum systems and pulling them into the macroscopic world. At its heart, decoherence is a process of connection. Quantum objects lose their coherence precisely because they become too entangled with the world around them. And the larger or more complex something is, the faster it becomes woven into that web of interactions. That's why quantum behavior flourishes in isolation, but collapses under everyday conditions. Yet the deeper truth is this: everything, absolutely everything, remains quantum beneath the surface. The solidity, certainty, and stability we experience are emergent illusions built on top of a universe that is intrinsically probabilistic. Decoherence doesn't deny the quantum world, it reveals how the classical world rises gently out of it. In the end, decoherence is one of the great translators of nature. It speaks both languages, the soft, shimmering dialect of quantum possibility, and the grounded, structured language of classical reality. It shows how the two realms coexist, not as separate domains, but as layers of the same universe, each expressing itself depending on how deeply something is entangled with its surroundings. It's a reminder that even though you walk through a world of solid objects and definite outcomes, beneath that frozen surface lies an ocean of quantum motion, subtle, continuous, always humming. And the boundary between those two worlds, the place where the wave becomes the world, is shaped quietly and continuously by decoherence. Some theories suggest that maybe there's no separate moment where the wave function suddenly collapses. Instead, what looks like a collapse might simply be decoherence doing its quiet work, spreading quantum information into the environment so thoroughly that the alternative outcomes become unreachable, invisible, effectively erased. It's not that the universe picks one version of events and discards the others. It's that the unused possibilities get drowned in the vast noise of reality. Like a lone echo swallowed by the forest, the alternatives don't disappear. They just melt into the background where no experiment can recover them. And yet, decoherence, as powerful as it is, doesn't answer every question. It doesn't tell us why a specific outcome appears when we finally take a measurement. It doesn't settle the old debate about what the wave function really is, an element of reality or simply a predictive tool. But it does reveal why our everyday world looks solid, stable, familiar. It shows that the classical world isn't separate from the quantum world. It's a filtered version of it, shaped by constant entanglement with everything around us. So when you grasp a cup or turn a door handle, decoherence is the silent reason those objects behave reliably. It turns a universe full of shimmering possibilities into something that feels like a firm handshake. No sparks, no drama, just the gentle fading of quantum potential until only a single stable outcome remains. And yet, just when you think you've made peace with quantum strangeness, the universe pulls the curtain back a little further. Imagine an experiment so delicate, so counterintuitive, that simply choosing when to observe seems to ripple backward through time, influencing what happened moments earlier. It sounds impossible, but this is exactly the mystery explored in the delayed choice experiments and their even stranger cousin, the quantum eraser. Let's return to the familiar double slit scenario. Fire photons or electrons at two slits, and if you don't check which slit they used, you get the classic interference pattern, a signature of wave like behavior. But if you watch the path even gently, even indirectly, the interference vanishes. The particles act like tiny bullets. Simply having the information makes the difference. Now twist the setup. In John Wheeler's delayed choice experiment, you let the particle pass through the slits without measuring its path. But after it has already gone through, you reserve the right to decide whether you want to know which slit it used. Only after the particle has crossed the slits do you choose whether to observe the path or not. And somehow the pattern on the screen reflects your choice, even though your decision came after the particle should have decided how to behave. If you choose to measure the path, the interference disappears. If you choose not to, the interference appears. It's as if the particle doesn't commit to being a wave or a particle until you decide what you're going to do, even if your decision happens a moment too late. Time in these experiments starts to feel strangely flexible, but physicists weren't done. They decided to push the mystery further with the quantum eraser. In this version, you do mark the particles so you could know their path, which destroys the interference. But later, sometimes even after the particles hit the detector, you erase that path information using a clever optical trick. And when you erase the witch path data, the interference comes back retroactively. The particles behave as if they had always been waves, as if the knowledge of their path had never existed, even though it briefly did. This bizarre behavior suggests a radical possibility. Quantum events don't fully settle into a single version of reality until all information about them is accounted for, not just the detection itself, but what we choose to do with the information afterward. It's like a time stretched version of Schrodinger's cat. Not only is the cat in limbo until you open the box, but the nature of its past, alive or dead, depends on what you decide to keep or erase after observing it. So, what does all this mean? One interpretation is that information, not matter, is the real backbone of the universe. Quantum outcomes don't crystallize until the questions we ask have definite answers. Before that, reality stays open, entangled, flexible, unfinished. And yet, as astonishing as it sounds, these experiments don't let us send messages to the past. They don't violate the classical arrow of time in any practical way. The universe preserves causality on large scales. But beneath that surface, in the deep quantum underlayer, the rules of cause and effect appear softer, more interconnected, more holistic than we ever imagined. It's not that quantum physics allows you to rewrite history, it's that history isn't fully written until the entire quantum story, including what we choose to measure or ignore, is complete. The universe doesn't run like a rigid machine. It behaves more like a web where meaning emerges only when all its strands are woven together. Some physicists try to tame the strangeness of delayed choice experiments by describing them not as backward causation, but as a network of correlations woven through the entire experimental setup. In this view, the particle isn't anticipating the future. It isn't whispering with tomorrow. It's simply part of a system where your final choice determines which patterns nature allows you to see. Others embrace a block universe perspective. The idea that past, present, and future all coexist in a single, timeless structure, like every frame of a film reel existing at once. In that interpretation, your future choice doesn't reach backward. It was always embedded in the geometry of the experiment from the beginning. And then there are those who avoid the philosophical maze entirely, shrugging with a quiet, pragmatic, shut up and calculate. Their view is that the universe isn't obligated to align with our intuitions about time sequence or logic. It behaves the way it behaves, and our discomfort is a reminder that our classical brains evolved to navigate apples and chairs, not probability waves and entangled histories. What delayed choice and quantum eraser experiments reveal isn't a breakdown of physics, but a deeper richness beneath it. They show us that the quantum realm doesn't mimic the familiar world in miniature. It plays by a subtler rhythm, a logic that's less linear, less local, and far stranger than we grew up believing. So, if time occasionally feels like it bends, blurs, or misbehaves, just remember on the quantum scale, it probably does exactly that. And now, if you zoom inward past galaxies, past molecules, past atoms, you eventually reach a domain where precision evaporates into something softer. A landscape where certainty is no longer the currency of existence, where outcomes emerge from clouds of probability rather than predetermined paths. In this deep quantum terrain, particles don't come with fixed positions or fixed fates. They inhabit a shimmering spectrum of possibilities until the moment you ask a question. And even then, what collapses into your detector is only one result from a cosmic lottery. This randomness is not an illusion. It's not a placeholder for missing data. According to the mathematics of quantum mechanics, it's fundamental. It's built directly into the structure of reality. Einstein famously resisted this view. God does not play dice with the universe. He said, insisting that hidden variables must exist some deeper layer of order beneath the quantum fog. But decades of theory and experiment have consistently shown no sign of such hidden instructions. The quantum dice seem to be real. In classical physics, the future unfolds like a perfect machine. If you know the initial conditions precisely enough, every position, every velocity, you can predict every moment that follows. But the quantum world dissolves that certainty. What replaces it is the wave function, a mathematical object that encodes all possible outcomes. When you measure, the wave function collapses, and one possibility becomes the event you experience. But which one becomes real isn't dictated by anything classical, it's genuinely random. Some interpretations try to rescue determinism by spreading the outcomes across many universes. In the many worlds picture, every possibility happens just not to you in this branch. Everywhere else, in countless versions of reality, other outcomes unfold. But despite this cosmic abundance, your subjective experience still contains uncertainty. You cannot predict which branch your awareness will follow. The randomness remains simply reframed. This raises philosophical questions that stretch far beyond physics. If randomness is built into the universe's foundations, what does that mean for cause and effect, for free will, for the nature of natural law? But there's a subtle beauty here. Quantum randomness isn't chaos, It isn't anarchy. In fact, quantum predictions are among the most precise in all of science. The probabilistic structure is exquisitely ordered. QED, for example, predicts the magnetic moment of the electron to more than 10 decimal places, an accuracy so extreme it's almost unnerving. So while each event is unpredictable, the collective behavior of many events becomes astonishingly reliable. That's why your coffee mug doesn't quantum tunnel through the table, even though individual particles can. The statistical smoothness of large numbers builds the classical world. In this sense, randomness is not a flaw in the universe, it's a feature, a flexibility woven into the fabric of reality, allowing creation, variation, evolution, and perhaps even consciousness to emerge. The universe isn't following a rigid script, it's exploring, improvising, allowing for novelty inside a framework that is still breathtakingly precise. And somewhere between the silence of probability and the solidity of measurement, between the quantum dice and the classical world, they collectively give rise to reality, unfolds exactly as it must, uncertain in its details, ordered in its structure, and endlessly alive with possibility. Some physicists try to soften the shock of delayed choice experiments by reframing them not as mysterious whispers from the future, but as patterns of correlation woven throughout the entire system. In that view, the particle isn't peeking ahead in time. It isn't waiting for your later decision. It's simply embedded in a web where the final configuration determines which version of reality becomes visible to you. Others prefer a broader, almost serene perspective, a block universe where past, present, and future sit side by side in a single, timeless panorama. In that picture, your future choice doesn't travel backward to rewrite anything. It was always part of the full geometry of the experiment, just another thread in a tapestry already complete. And of course, there are those who sidestep the philosophy entirely and settle into a quiet, practical stance. Shut up and calculate. To them, the universe isn't here to satisfy our intuitions about linear time or neat sequences. Our biological senses evolved to track lions and fruit, not quantum waves and entangled histories. What delayed choice and quantum eraser experiments really show us is not the failure of physics, but the deeper architecture beneath it, an architecture far less local, far less orderly, and far more subtle than the world we navigate with our hands and eyes. So when time feels like it bends, hesitates, or loops around itself, remember on the quantum scale, that might not be an illusion at all. And if you continue zooming inward past planets, past molecules, past the quiet shells of atoms, you eventually reach a level where certainty dissolves into something softer and more fluid. Here, position and momentum stop behaving like fixed attributes and instead blur into overlapping probabilities. A particle doesn't sit at a location waiting for you to find it. It spreads across possibilities, inhabiting a spectrum of potential states until the moment your question forces it to commit. And even then, the answer you receive is drawn from a fundamentally random process. This randomness isn't a placeholder for ignorance. It isn't the result of missing details the theory hasn't uncovered. It is built directly into the mathematics, into the very structure of the quantum field itself. Einstein fought this idea to the end. The notion that the universe might hinge on probabilities rather than precise mechanisms felt intolerable to him. God does not play dice, he said, insisting that some deeper order must be hiding beneath the uncertainty. But experiment after experiment has shown that the randomness is real, or at least indistinguishable, from something truly fundamental. In classical physics, the future is a clean extrapolation of the present. Give the universe its initial conditions, every velocity, every angle, every position, and you get an exact blueprint of tomorrow. Quantum mechanics dissolves that picture. Instead of certainty, it offers a wave function, a beautifully compact mathematical description of all possible outcomes. When you measure, that wave of possibilities collapses and gives you a single result. But the particular outcome you see isn't determined in advance. It arrives through pure quantum randomness. Some interpretations, like the many worlds view, try to restore determinism by spreading every possible result across an infinite branching of universes. In that framework, nothing is truly random. Each outcome happens somewhere. But even if the branching is real, your awareness still experiences uncertainty. You don't know which branch you'll inhabit until the measurement plays out. The unpredictability remains from your perspective, simply woven into a larger cosmic structure. This opens the door to deeper questions. If randomness is woven into the foundations of reality, what does that mean for causality, for the flow of time, for the idea of free will? But here lies a quiet beauty. Quantum randomness is not chaos. It's not disorder. It's a finely tuned probability landscape that produces predictions of astonishing precision. The magnetic moment of the electron, for example, matches QED calculations to more than 10 decimal places, a level of accuracy almost beyond comprehension. So even though each quantum event is unpredictable, the collective behavior of many events becomes beautifully regular. That's why your desk stays where it is. That's why objects don't dissolve into probability fog. Ensembles of quantum randomness create the smooth, steady classical world. In this way, randomness is not a defect in the universe, it's a dimension of freedom, a softness built into the fabric of existence that allows reality to breathe, evolve, and generate novelty. Without it, the universe would be rigid, mechanical, and lifeless. With it, new forms emerge, systems adapt, consciousness evolves. Somewhere between pure probability and the solidity of measured outcomes, between the shimmering quantum possibility and the stable classical world, it gives rise to the universe, creates itself moment by moment. Uncertain in details, precise in structure, and endlessly alive in its unfolding. Whether you're waiting for a medical result, hoping for a callback after an interview, or simply wondering whether tomorrow will bring rain or sun, you've probably noticed something subtle. We often live inside our own kind of quantum superposition. Hope on one side, worry on the other. Possibility layered over possibility. Nothing decided, nothing fixed. Just a quiet cloud of outcomes resting above us until time, choice, or circumstance nudges reality into focus. And perhaps that's one of the hidden gifts of quantum mechanics. It doesn't tell us the world is chaotic or meaningless. It simply whispers that reality isn't obligated to reveal itself all at once, that beneath the surface there is softness, openness, room to breathe. If certainty isn't guaranteed, then neither is limitation. If the world doesn't collapse into a single outcome until the moment it's observed, then possibility is always alive, somewhere in the background, glowing faintly like a distant star. Even the word quantum carries a quiet poetry. From the Latin quantus, how much energy, how much light, how much change can occur in one discrete leap. It's a reminder that transformation doesn't always happen continuously. Some changes come in thresholds, in steps, in sudden transitions from one state to another, and maybe that mirrors the human experience more closely than we admit. You don't dream in tiny increments. You don't drift into imagined landscapes atom by atom. You leap instantly into worlds that weren't there a moment ago. When you return, you may forget the details, but you carry the imprint, the feeling of possibility. Quantum physics feels like that, like waking from a dream and suddenly realizing the universe is far stranger and far more wonderful than the version you learned in school. And yes, that strangeness can be a little unsettling. We like straight lines. We like neat answers. We like leading cleanly into effect. Certainty is comforting, but maybe certainty is also a bit overrated. Maybe there's value in wandering through a world where some questions don't resolve immediately, where outcomes take their time, where curiosity has space to bloom because not everything is already decided. Richard Feynman once said with equal parts humor and honesty, I think I can safely say that knows he understands quantum mechanics. And he didn't mean that as a failure. He meant that quantum physics isn't something you comprehend the way you understand a simple equation. It's something you accept, like a piece of art or a dream or a feeling that refuses to be captured fully in words. The math works, the predictions are flawless, but the meaning slips through your fingers like water because the universe was never designed to fit neatly into human logic. It simply is. So, as we drift through these quiet quantum ideas together, maybe the most important insight isn't about electrons or wave functions. Maybe it's about perspective, about learning to see uncertainty not as a flaw, but as an invitation, a reminder that not knowing is part of being alive, that mystery is not a problem to solve, but a space to rest in, because we are part of a cosmos that is still unfolding, still choosing, still shimmering, with probabilities waiting to become experiences. A cosmos where even the emptiest vacuum carries hidden energy, where time bends softly around possibility, where light forgets occasionally how to behave, and where reality itself dreams in ways we are only beginning to sense. Thank you for wandering through this with me. Whether you're wide awake, slowly drifting, or already dissolving into your own dream world, we've traveled far tonight through double slits and imaginary cats, through rippling quantum fields and clocks that don't tick quite the way they should. We've met particles behaving like waves, and waves masquerading as particles. And somewhere in that journey, something quiet shifted. The universe didn't become simpler, but it perhaps became gentler, more wondrous, more alive. because the world beneath the world, the quantum world, is softer than it looks. Not rigid, not mechanical, but luminous with possibility. And you are made from that same luminous fabric. The particles in your skin, the photons entering your eyes, the oxygen filling your chest, every bit of it follows the very rules we've been talking about. You are not separate from the strangeness. You are the strangeness. A living configuration of quantum fields temporarily gathered into a shape that can wonder, listen, and dream. And maybe as you lie there listening, whether curled beneath a warm blanket or simply staring at the ceiling, you can feel just a little of that vastness inside you too, wherever you find yourself right now. I hope this journey left you with something gentle to hold on to, maybe a spark of wonder, maybe a quiet pause, maybe just a softer sense of being here. Because when we look into the foundations of matter and ask, what is real quantum physics, doesn't hand us a final definition. Instead, it offers a shifting reflection, a reminder that understanding something deeply doesn't always require fully grasping it, that questions can carry as much beauty as answers. That uncertainty isn't a flaw in the universe, it's part of its architecture. It's natural to wish the cosmos would explain itself more clearly, to want the rules written in simple lines, to hope everything will add up neatly if we stare long enough. But within this tangled uncertainty, there's another kind of comfort, a softer one, a truth that says you don't need perfect clarity to feel grounded. You don't need every mystery solved to feel at home in the moment you're in. Because even if the particles themselves refuse to sit still, you are here. This breath is here. The weight of your body easing into stillness is here. The thought drifting past brief, fleeting real is here. And all of that in its own quiet way is quantum too. And it's enough. So thank you for offering your attention, your patience, and your curiosity to this little exploration. Thank you for letting the strangeness unfold without needing to tame it, for sitting with the not knowing and allowing the mystery to be a place you can rest instead of something you must chase. And if sleep has already taken over, perfect. Let it. The quantum world will still be waiting for you when you return. From the sleepy scientist, good night.